There is something unsettling about places that have survived longer than memory itself. Long after the people who built them vanished, these monuments remain exactly where they have always been, weathered by time, yet untouched by explanation. They stand on lonely mountaintops, beneath shifting deserts, inside cliffs, and deep within forgotten valleys, each one preserving a fragment of a story that was never fully told. Archaeologists continue to uncover remarkable clues, but every answer seems to lead to an even greater mystery. The stones have never moved. The silence has never broken. Only our questions have changed. And perhaps that is why the ancient world continues to fascinate us. Because the closer we get to understanding it, the more it reminds us how much of our own history is still waiting in the shadows. Barbegal Mill Complex in southern France is known as the ancient industrial site where gravity itself became the engine. Hidden on a limestone hillside a few kilometers northeast of Arles, this Roman installation transformed nothing more than elevation, flowing water, and carefully calculated geometry into one of the most sophisticated mechanical systems of the ancient world. Unlike monuments built to inspire admiration, Barbegal was designed to work continuously, converting the natural fall of water into productive energy with remarkable efficiency. Even after more than 18 centuries, archaeologists still debate how Roman engineers achieved such extraordinary control over a force as unpredictable as moving water, raising the possibility that gravity here was not simply a source of power, but a technology deliberately engineered and managed with a level of precision that remains difficult to explain. The ruins first attracted scholarly attention during the 19th century, when stone foundations and fragments of an aqueduct were identified on the hillside. But the true importance of the site only became clear after systematic excavations throughout the 20th century revealed an industrial complex unlike any other known from the Roman Empire. Archaeologists uncovered the remains of 16 watermills arranged in 2 parallel rows descending the slope, each driven by water arriving from the Roman aqueduct network that once supplied nearby Arles. Based on the surviving foundations, wheel pits, channels, and engineering calculations, researchers estimate that the complex could produce approximately 4.5 to 5 metric tons of flour every day, enough to supply bread for roughly 20,000 to 30,000 people, depending on consumption estimates. Such capacity made Barbegal one of the largest known mechanical production facilities anywhere in the ancient world. Yet the machinery itself was never powered by animals, slaves, wind, or combustion. Every movement depended entirely upon gravity acting on water descending the hillside. That remarkable achievement immediately leads to the greatest mystery surrounding the complex, because water is one of the least stable energy sources imaginable. A slight increase in flow accelerates a wheel beyond its optimal speed, reducing grinding efficiency and placing destructive stress on wooden gears and millstones, while even a modest reduction in flow can slow the machinery until production nearly stops. Modern hydroelectric facilities rely on mathematical modeling, pressure measurements, adjustable gates, and automated controls to maintain consistent performance. But Roman engineers possessed none of those technologies. Nevertheless, every surviving indication suggests that the mills at Barbegal operated with surprising stability over an extended period. The obvious question, therefore, becomes not whether gravity powered the factory, but how gravity itself was controlled. Unlike many Roman mills that simply directed water toward a single wheel, Barbegal forced one stream through an entire sequence of machines. Water entered the uppermost channel before falling onto the first wheel, then continued into another carefully shaped channel leading to the second wheel, repeating the process until the final mills at the bottom of the slope. Every drop therefore performed mechanical work multiple times before leaving the complex. Such an arrangement appears simple at first glance, yet it introduced an engineering problem of enormous complexity, because every wheel affected the water available to every wheel below it. If one section received too much water, the remaining mills would suffer reduced flow. If turbulence developed inside a channel, efficiency throughout the cascade could decline. In effect, 16 separate machines had to behave as one coordinated system despite being connected only by gravity and moving water. Recent archaeological investigations have revealed that the channels themselves may hold the answer, although not a complete one. Exceptionally preserved carbonate deposits that accumulated on the interior surfaces of the original wooden flumes survived after the timber decayed, creating mineral casts that recorded the exact geometry of the channels. By scanning these deposits with high-resolution three-dimensional imaging, researchers reconstructed flumes unlike those used in ordinary Roman watermills. Instead of simple straight troughs, several channels narrowed toward their outlets while others curved in carefully controlled ways that accelerated and redirected the flow before it struck the paddles below. Hydraulic engineers studying these reconstructions concluded that the unusual geometry intentionally optimized water velocity, reduced unnecessary turbulence, and concentrated kinetic energy exactly where it produced the greatest rotational force. The astonishing implication is that Roman builders had discovered through observation and experimentation how subtle changes in channel shape could regulate moving water centuries before the mathematical principles of fluid dynamics were formally described. That conclusion only deepens the mystery, because no surviving Roman manuscript explains how such designs were calculated. Vitruvius described general hydraulic principles in De Architectura, yet nothing approaching the extraordinary configuration preserved at Barbagal appears in his writings or in any other known technical text. The dimensions of individual channels differ slightly from one another rather than following identical templates, suggesting that each section may have been adjusted to compensate for changes in elevation, remaining water volume, or wheel performance farther down the hillside. Modern computer simulations indicate that even differences measured in only a few centimeters could significantly alter discharge velocity and energy transfer. Whether Roman engineers reached these solutions through generations of accumulated practical experience, repeated experimentation, or mathematical methods now completely lost, remains unresolved. What survives is evidence that someone understood gravity not merely as a downward force, but as a controllable mechanical resource capable of being distributed with extraordinary precision. Evidence collected during the past decade has introduced another unexpected puzzle. Scientists analyzed the microscopic layering inside the carbonate deposits using isotope measurements and seasonal growth patterns, effectively allowing the mineral itself to record the operational history of the mills. The results indicated that the complex did not function continuously throughout the year, as long believed. Instead, the deposits suggest periods of regular operation alternating with intervals when water flow ceased altogether. This seasonal rhythm challenges earlier assumptions that Barbagal simply supplied daily flour for the population of Arles. If the mills were inactive during parts of the year, their purpose may have been more specialized than previously imagined. One increasingly discussed hypothesis proposes that the flour produced here supplied hardtack, the dense, dry biscuit carried aboard Roman merchant ships and naval vessels, because it remained edible for months. Arles occupied a strategic position connected to Mediterranean trade routes, making large-scale production for maritime transport entirely plausible. Yet this explanation creates its own unanswered questions, because archaeologists have never identified industrial baking facilities of corresponding capacity immediately adjacent to the mills. Another possibility suggests that production responded to seasonal grain deliveries, regional demand, or state-controlled distribution systems that remain poorly understood. None of these interpretations fully accounts for every archaeological observation, leaving the true economic role of Barbagal uncertain despite decades of investigation. Equally intriguing is the fact that nothing quite like Barbagal appeared elsewhere in the Roman Empire. While thousands of watermills are known from Britain to Syria, none match its 16 cascading wheels and coordinated hydraulic system for large-scale production. Its uniqueness may be due to rare topography, high maintenance demands, or lost technical knowledge. Whatever the cause, Barbagal remains a rare example of Roman hydraulic engineering, where gravity was harnessed as an early form of large-scale automation. In the Taurus Mountains of southwestern Turkey, Sagalassos turned gravity into an invisible machine nearly 2,000 years ago. Long before pumps, engines, or electricity, a city standing between approximately 1,450 and 1,700 meters above sea level sustained monumental fountains, vast bath complexes, workshops, and thousands of residents using nothing more than carefully controlled differences in elevation. Excavations revealed that gravity was never simply a natural force here. It was engineered, measured, restrained, and distributed with a level of precision that continues to challenge archaeologists and hydraulic engineers alike. Modern understanding of this forgotten network began after systematic archaeological investigations intensified during the late 20th century under an international research project led by the Catholic University of Leuven. Beneath collapsed streets and monumental buildings, researchers uncovered extensive pipelines, settling basins, distribution tanks, reservoirs, and hydraulic installations that once carried mountain spring water across the entire city. Even more remarkable, restoration of the Antonine Nymphaeum demonstrated that parts of the original hydraulic design still function as intended. Once water was reintroduced, the monumental fountain operated again using only gravitational pressure, proving that the ancient calculations had remained effective despite nearly 18 centuries of abandonment. That discovery immediately raised a far more difficult question than how the Romans transported water. The real mystery is how they controlled it. Sagalassos occupied an exceptionally steep mountainside, where differences in elevation could generate enormous hydraulic pressure. Physics is straightforward. Every 10 meters of vertical water column produces approximately 1 bar of pressure. A descent of 100 meters creates roughly 10 bar, while 200 meters approaches 20 bar, pressures capable of fracturing ordinary ceramic pipelines or forcing joints apart if left unmanaged. Yet excavated sections of the city's water network show remarkably little evidence of catastrophic pressure failures despite centuries of continuous operation. The survival of numerous terracotta pipes, stone conduits, and distribution structures suggests that ancient engineers possessed a practical understanding of hydraulic pressure far beyond what written records explicitly describe. This is precisely where the greatest unresolved mystery begins. No complete ancient manual explains how Roman engineers at Sagalassos continuously reduced pressure before it reached vulnerable sections of the network. Archaeologists have identified reservoirs, settling basins, and distribution chambers positioned throughout the city, but the surviving remains do not fully explain how pressure was regulated across every elevation change. One prevailing interpretation argues that each basin functioned as a hydraulic brake tank, allowing water to lose excess pressure before entering the next section of pipeline. Another proposes that carefully calculated changes in pipe diameter moderated flow velocity while maintaining adequate discharge. Others suggest combinations of concealed overflow chambers, pressure relief outlets, and sequential storage pools distributed across the mountainside. Because significant portions of the system remain buried beneath later collapsed deposits, none of these models can yet be confirmed in their entirety. What survives instead is the remarkable physical evidence that whatever solution was employed, it worked with extraordinary reliability. The mystery becomes even deeper when considering the city's monumental fountains. The Antonine Nymphaeum was not a simple basin collecting water from above. Rising roughly 9 meters high and decorated with elaborate architectural facades, it produced multiple cascades and ornamental displays, requiring a carefully balanced hydraulic supply. Excessive pressure would have damaged the structure, while insufficient pressure would have reduced the flowing water to little more than a trickle. Achieving the correct balance without mechanical pumps required calculations linking reservoir elevation, conduit gradients, flow resistance, and outlet dimensions into a single integrated system. Modern hydraulic equations describe these relationships through pressure head, gravitational potential energy, and friction loss inside pipelines. Yet the builders of Sagalassos accomplished similar practical results using observation, geometry, and accumulated engineering experience nearly 2 millennia before fluid mechanics became a formal scientific discipline. Equally remarkable is the consistency of water distribution throughout a city built on sharply changing terrain. Streets climbed steep slopes, terraces supported public buildings at different elevations, and residential districts occupied irregular mountainside platforms. Under such conditions, gravity naturally accelerates water downhill, creating unequal pressure throughout the network. Lower neighborhoods normally receive excessive flow, while higher sections risk insufficient supply. Excavated evidence, however, indicates that public baths, fountains, and urban districts all maintained dependable access to water over long periods. This suggests that the hydraulic network was divided into carefully balanced sectors rather than operating as one continuous pipeline. Each reservoir appears to have served not merely as storage, but as a recalibration point, where gravity itself was effectively reset before water continued toward the next destination. The entire mountain therefore functioned less like a passive landscape and more like an enormous gravity-powered processor, continuously regulating hydraulic energy. Another unresolved question concerns accuracy. Modern engineers rely on laser surveying equipment capable of measuring gradients to fractions of a millimeter. Roman surveyors possessed no electronic instruments, yet the conduits at Sagalassos maintained gradients sufficient to sustain continuous flow without allowing sediment accumulation or destructive turbulence. Water moving too slowly deposits suspended particles that gradually block pipelines. Water moving too rapidly erodes joints, damages channels, and increases structural stress. Maintaining the optimal gradient over hundreds of meters across fractured limestone terrain required extraordinary surveying precision. Historians know Roman engineers employed instruments such as the chorobates and groma, but whether these tools alone could repeatedly achieve the necessary accuracy across such difficult topography remains an active subject of debate. The surviving hydraulic performance suggests measurement techniques whose practical precision exceeded what many researchers once believed possible. Geological conditions added another layer of complexity. Sagalassos occupies an active tectonic region where earthquakes periodically altered the landscape throughout antiquity. Ground movement normally disrupts buried pipelines by changing slopes, separating joints, or creating fractures that rapidly leak water. Yet excavations reveal numerous conduits remaining aligned with surprisingly limited structural failure. Some researchers believe flexible joints, segmented construction, and modular replacement strategies allowed damaged sections to be repaired without dismantling the entire network. Others argue that careful routing through stable bedrock reduced geological stress from the beginning. Since much of the underground infrastructure has yet to be exposed, the exact engineering strategy remains uncertain, leaving another important chapter of the system hidden beneath the mountain. Perhaps the most fascinating aspect of Sagalassos is that gravity itself became programmable. Every reservoir changed pressure, every basin modified energy, every conduit transformed elevation into controlled motion. Instead of fighting nature, the city's engineers converted differences in height into a renewable source of mechanical work that required no fuel and produced no moving parts. The network stored potential energy in elevated water, released it through carefully measured gradients, stabilized it inside distribution chambers, and delivered it precisely where urban life demanded. Long before hydraulic science received mathematical formulas, Sagalassos demonstrated that gravity could be treated as an engineered technology rather than merely a natural phenomenon. The tunnel of Eupalinos on the island of Samos, Greece, is known as one of the earliest places where gravity itself became a form of technology, carrying fresh water through the heart of a mountain more than 25 centuries ago without a single pump, wheel, or source of mechanical power. Hidden beneath Mount Castro, the tunnel stretches approximately 1,036 meters through solid limestone, while the water channel beneath it transformed nothing more than a gentle downward slope into an engineering system capable of supplying an entire fortified city. Few ancient structures demonstrate so clearly that the greatest machine available to early civilizations was not made of wood or bronze, but of the invisible force that pulls everything toward the earth. The tunnel remained forgotten for many centuries after the ancient city declined until the 19th century, when scholars studying the descriptions of the Greek historian Herodotus began searching beneath the mountain for the extraordinary work he had praised as one of the greatest engineering achievements of the ancient world. Excavations eventually revealed a remarkably preserved passage cut directly through the mountain together with the concealed water conduit running below its floor. Archaeological surveys, geological mapping, laser scanning, and modern engineering analysis have since confirmed that construction began around 530 to 520 BCE during the rule of Polycrates, the powerful tyrant of Samos, while the project itself was designed by Eupalinos of Megara, an engineer whose mathematical planning continues to astonish specialists today. The purpose of the tunnel appears straightforward until its technical details are examined. Fresh water originated from a spring on the northern side of the mountain before entering the underground conduit and flowing naturally toward the ancient city on the southern side. Nothing pushed the water except gravity, yet gravity alone could never guarantee a reliable supply. If the channel descended too steeply, flowing water would gradually erode the stone and increase turbulence, reducing long-term stability. If the slope became too gentle, sediment would settle on the bottom, eventually obstructing the channel and reducing the water available downstream. Every successful gravity-fed hydraulic system depends upon maintaining an extraordinarily delicate balance between elevation, velocity, discharge, and friction, principles described mathematically only thousands of years later, yet somehow applied here with remarkable effectiveness. This leads directly to the question that continues to challenge historians of engineering. How did builders working more than 2,500 years ago maintain an almost perfectly controlled gradient throughout a conduit extending for more than 1 kilometer beneath a mountain, Modern engineers rely upon precision optical instruments, laser levels, electronic surveying equipment, satellite positioning, and detailed topographic models before beginning similar work. None of these technologies existed during the 6th century BCE. Archaeologists have identified iron chisels, hammers, wedges, measuring cords, and plumb bobs as the principal construction tools, but these discoveries explain how the rock was removed rather than how the elevation was controlled with such consistency. Even a relatively small surveying error, repeated over hundreds of meters, could have produced stagnant pools, reversed flow, or sections where water simply failed to reach the city. Instead, the conduit functioned efficiently for centuries, demonstrating that the calculations governing its slope were fundamentally correct. Several hypotheses attempt to explain this achievement, although none completely accounts for every observation inside the tunnel. One possibility suggests that Eupalinos employed repeated water level measurements, exploiting the fact that standing water always establishes a perfectly horizontal reference surface. Another proposes systematic use of plumb lines, combined with carefully measured vertical offsets over short intervals before transferring those measurements throughout the excavation. Some researchers believe astronomical observations may have assisted in establishing the overall alignment before excavation even began, while others emphasize advanced geometric surveying derived from practical traditions that have left almost no surviving written record. Every proposal successfully explains part of the evidence, yet leaves important questions unanswered, ensuring that the precise surveying procedure remains one of the most fascinating unsolved problems in ancient engineering. The remarkable accuracy of the hydraulic gradient becomes even more extraordinary when considered alongside another famous feature of the project. Instead of excavating from one entrance until reaching the opposite side, workers began simultaneously from both ends of the mountain. Each team disappeared into solid limestone, carrying only simple tools, artificial light, and whatever measurements had been established before construction started. More than 1,000 meters later, the two excavations successfully met beneath the mountain, with surprisingly small positional error. Detailed surveys reveal that the final alignment was not absolutely straight, because Eupalinos intentionally introduced a calculated directional adjustment near the meeting point, rather than representing a mistake. Many engineers interpret this deviation as a deliberate strategy that increased the probability of intersection, even if minor surveying inaccuracies accumulated during excavation. The concept resembles modern engineering redundancy, where controlled flexibility is introduced specifically to compensate for unavoidable uncertainty. Equally revealing is the internal arrangement of the tunnel itself. Visitors walking through the main passage today are often surprised to discover that the water did not originally flow across the tunnel floor. Instead, the principal passage served as an access corridor, while the actual hydraulic channel occupied a narrower trench excavated below it. In several sections, this trench descended even deeper into the rock to preserve the required hydraulic gradient, despite variations in the mountain above. This two-level configuration allowed maintenance crews to inspect, clean, and repair the conduit without significantly disturbing water transport, demonstrating that long-term operation had been considered from the beginning rather than added after construction. Gravity therefore acted within a carefully engineered environment, instead of an ordinary ditch following the landscape. Geological conditions inside Mount Castro further complicated the project. Limestone formations rarely possess perfectly uniform hardness, and fractures, bedding planes, and natural joints continually alter excavation conditions. Builders, therefore, faced the dual challenge of preserving structural stability while simultaneously protecting the hydraulic profile below. Archaeological evidence shows that excavation techniques changed according to local rock quality, suggesting continuous adaptation instead of rigid repetition. Even so, the conduit maintained the gradual descent required for reliable flow despite these changing geological conditions, indicating that hydraulic planning remained the dominant priority throughout construction. The strategic purpose of placing the entire water system beneath the mountain has generated considerable discussion. Constructing an open aqueduct across the landscape would almost certainly have required less excavation and fewer laborers. Polycrates nevertheless invested enormous resources into driving a tunnel directly through solid rock, because Samos occupied a politically unstable region where sieges posed a constant threat. A surface canal could easily have been cut, poisoned, or captured by an attacking army, whereas a concealed gravity-fed conduit, protected beneath hundreds of meters of limestone, remained extremely difficult to locate or destroy. In this sense, gravity became more than a convenient natural force. It became an invisible component of military infrastructure, ensuring that water continued reaching the city even when the surrounding landscape became a battlefield. Comparisons with later hydraulic systems make the tunnel appear even more remarkable. Roman aqueducts achieved extraordinary precision centuries afterward, yet many relied upon extensive surface channels, bridges, and arcades that allowed engineers to monitor alignment continuously during construction. Eupalinos, instead, solved similar hydraulic problems almost entirely inside a mountain, where direct observation was impossible. The tunnel therefore represents not simply an early aqueduct, but one of history's earliest demonstrations that mathematical planning, geological understanding, surveying, and gravity could function together as an integrated technological system. Volterra, Tuscany, Italy. Hidden beneath a hilltop city that has stood for more than 2,300 years lies a network that transformed gravity into an invisible machine. Long before pumps, pressure systems, or mechanical engines existed, the people who built Volterra created underground passages that allowed water to travel exactly where it was needed, carrying away floods, protecting streets, stabilizing buildings, and quietly regulating daily life using nothing more than the constant pull of Earth's gravity. What survives today is not simply an ancient drainage system, but evidence that the Etruscans may have understood landscape engineering with a level of precision still difficult to explain. The existence of these underground works became clearer during restoration projects and archaeological excavations beneath the historic center throughout the 19th and 20th centuries, when workers repeatedly encountered carefully constructed stone-lined tunnels running below streets, walls, and public spaces. Later surveys using laser mapping, structural analysis, and modern archaeological recording revealed that many of these passages belonged to an organized hydraulic network rather than isolated drains. Some sections remain accessible beneath the medieval city, demonstrating that later Roman and medieval builders often incorporated the earlier Etruscan infrastructure instead of replacing it. This continuity alone suggests the original engineering remained reliable for centuries beyond the civilization that designed it. Understanding why the system functions so well begins with the landscape itself. Volterra rises roughly 550 meters above sea level on a steep ridge composed of sandstone, clay, and marine sediment that has always been vulnerable to erosion and landslides. Heavy seasonal rain falling on such terrain would naturally rush downhill with destructive force unless carefully controlled. Instead of resisting gravity, the Etruscans appear to have embraced it as the central operating principle of the entire settlement. Streets, open spaces, retaining walls, and underground conduits worked together so rainwater entered the drainage network almost immediately before being guided safely toward lower elevations. Gravity performed every stage of the process without human intervention, turning the city itself into a machine powered by elevation differences. The remarkable feature is that the network does not appear to rely on steep channels that simply allowed water to fall as quickly as possible. Modern hydraulic engineering shows that excessive gradients increase erosion, damage stone joints, and create turbulent flow capable of undermining tunnels. Insufficient gradients, however, allow sediment to settle until passages become blocked. The ancient builders consistently avoided both extremes. Archaeological measurements indicate that surviving channels maintain gentle, carefully controlled inclinations that keep water moving while minimizing structural stress, a balance that modern engineers still pursue when designing gravity-fed drainage systems. The precision becomes even more impressive because the tunnels twist beneath irregular bedrock rather than following perfectly straight alignments. This raises the greatest unanswered question surrounding Volterra. How did the Etruscans measure those gradients with such consistency? Today, engineers establish slopes using laser levels, total stations, satellite positioning, digital terrain models, and computer calculations capable of detecting differences measured in millimeters. None of these tools existed during the 4th or 3rd centuries BC, when much of the underground infrastructure was constructed. Archaeologists have proposed simple instruments including plumb lines, measuring rods, water-filled channels, and wooden sighting frames. Yet none fully explains how surveyors maintained accurate inclinations through long underground passages that changed direction repeatedly while remaining hidden beneath solid ground. Once excavation progressed beyond the entrance, direct visual reference to the surrounding landscape disappeared completely, leaving builders dependent upon measurements that somehow remained reliable over distances extending hundreds of meters. No surviving Etruscan texts describe the surveying methods, no instruments have been conclusively identified, and no reconstruction has reproduced the same level of accuracy across an entire urban drainage network. The calculations existed, but the procedure behind them has vanished. As researchers examined the tunnels more closely, another pattern emerged that deepened the mystery. The passages frequently avoid the weakest geological layers beneath the city, even though those softer sediments would have been easier to excavate. Instead, builders often directed the tunnels through stronger sandstone, capable of supporting stable roofs over extremely long periods. Modern geological mapping confirms that Volterra rests upon alternating layers of competent rock and unstable clay, the latter prone to deformation and collapse when saturated with water. Choosing the correct route would have required more than simple observation at the surface, because many geological boundaries remain concealed underground. Whether the builders recognized subtle changes in rock texture during excavation or possessed a practical understanding of local geology developed through generations of experience remains uncertain, but their decisions dramatically increased the survival of the network. The construction techniques themselves reveal similar sophistication. Large stone blocks were carefully fitted to create channels resistant to displacement while allowing water to pass with minimal resistance. Curves within the tunnels tend to be gradual rather than abrupt, reducing hydraulic turbulence that would otherwise slow flow and increase erosion. Passage dimensions remain surprisingly consistent, despite being excavated through varying geological conditions, suggesting standardized planning rather than improvised digging. Every detail indicates that the builders were not merely removing unwanted water, but actively controlling its speed, direction, and energy. In modern terminology, they were managing hydraulic behavior without equations, pumps, or powered machinery, relying entirely upon gravity and geometry. Equally remarkable is how long the system continued to function. Volterra experienced Roman occupation, medieval reconstruction, Renaissance expansion, earthquakes, natural erosion, and continuous urban development, yet significant portions of the ancient drainage network survived beneath all these later layers. In several locations, medieval builders simply connected new drains to existing Etruscan passages instead of abandoning them, an extraordinary acknowledgement that infrastructure created centuries earlier still performed its intended purpose. Such longevity cannot be explained by durable stone alone. Hydraulic structures usually fail because gradients change, sediment accumulates, or surrounding soil shifts. The fact that much of the network avoided these failures suggests the original surveying and engineering were exceptionally accurate. The broader layout of the city introduces another possibility. Rather than designing streets first and drainage afterward, the Etruscans may have planned both simultaneously as parts of one integrated system. Rain falling onto roofs naturally entered sloping streets. Public spaces directed runoff toward collection points. Retaining walls stabilized the terrain while channeling water, and underground tunnels carried the flow safely downhill before destructive pressure could accumulate beneath the settlement. Every component depended on gravity acting predictably from the highest point to the lowest. The city therefore functioned less like a collection of independent buildings and more like a carefully calibrated hydraulic landscape, where elevation itself became the driving force. Comparisons with later Roman engineering make Volterra even more intriguing. Roman aqueducts are celebrated for maintaining gradients of only a few centimeters over long distances, achievements rightly regarded as masterpieces of ancient surveying. Yet the hydraulic principles demonstrated beneath Volterra appeared centuries earlier within an Etruscan context. Historians continue debating how much Roman hydraulic engineering inherited from Etruscan knowledge, because written evidence remains scarce, but the surviving tunnels indicate that sophisticated gravity-based infrastructure was already well established before Rome dominated the Italian peninsula. If the Romans refined these methods, they may have built upon foundations laid by engineers whose techniques were never recorded. Phaistos Palace on the island of Crete, Greece, hides one of the oldest examples of gravity functioning as an invisible machine rather than simply a force of nature. Long before pumps, valves, or mechanical engines, an entire royal complex appears to have been designed so water could travel exactly where its builders intended, using nothing more than changes in elevation. Excavations led by the Italian archaeologist Federico Halbherr, beginning in 1900, uncovered far more than monumental staircases and ceremonial courtyards. Beneath the limestone floors lay an intricate network of stone-built drainage channels, underground conduits, settling basins, and carefully positioned outlets revealing that hydraulic engineering had been embedded into the palace from its earliest construction during the Protopalatial period around 1900 BC and later rebuilt after the destructive earthquake around 1700 BC. Every new discovery has strengthened an extraordinary conclusion. Gravity itself was transformed into the operating mechanism of the palace. Yet the knowledge required to achieve this still raises questions that archaeology cannot completely answer. The palace occupies a commanding hill overlooking the fertile Messara plain at an elevation of approximately 100 meters above sea level. That position offered strategic advantages, but its engineering value may have been even greater. Instead of forcing water to climb or relying on artificial pressure, the architects exploited the natural slope of the hill so every courtyard, corridor, staircase, roof, and storage area became part of a continuous hydraulic system. Rainwater falling onto paved surfaces entered narrow stone gutters before reaching larger underground channels. Wastewater from workshops and residential quarters joined separate conduits before eventually leaving the complex through carefully controlled exits. Modern hydraulic engineers recognize that such a system depends entirely on maintaining precise gradients. If the slope is too gentle, sediment accumulates and blocks the channel. If the slope is too steep, flowing water accelerates enough to erode masonry joints and undermine foundations. Achieving the correct balance requires careful calculation, making the palace appear less like a collection of buildings and more like a machine whose moving component was water itself. This leads directly to the greatest unresolved mystery surrounding Phaistos. How did Minoan engineers calculate these gradients without precision surveying instruments? The palace was constructed more than 3,800 years ago, centuries before the mathematical methods associated with classical Greek geometry and millennia before optical levels or modern surveying equipment existed. Archaeologists have recovered no measuring devices capable of determining elevation differences with millimeter accuracy. Yet many drainage channels maintain remarkably consistent inclinations over considerable distances despite crossing multiple construction phases. Even a deviation of only a few centimeters across several tens of meters could have created stagnant pools, flooding, or destructive turbulence. The remarkable efficiency of the surviving channels suggests that their builders understood practical hydraulic behavior with impressive accuracy, but the method remains unknown. Some researchers propose that water-filled trenches or suspended plumb lines were used to establish reference levels, while others believe generations of empirical experimentation gradually refined construction techniques. Neither explanation fully accounts for the consistency observed throughout the complex, leaving open the possibility that the Minoans possessed surveying practices that have disappeared completely from the archaeological record. As researchers examined the drainage network more closely, another remarkable characteristic became apparent. The hydraulic system does not appear to have been inserted after construction to solve problems discovered later. Instead, the drains pass beneath walls, courtyards, staircases, magazines, and ceremonial spaces in ways indicating that they were incorporated into the architectural blueprint from the beginning. This required the designers to predict where rainwater would collect, how quickly it would flow across stone pavements, how much runoff could be generated during intense Mediterranean storms, and how every section of the palace would interact with every other section. Such integrated planning resembles principles used in modern urban drainage design, where the movement of water determines the organization of streets and buildings rather than being treated as an afterthought. For a civilization flourishing during the Middle Bronze Age, this level of coordinated planning remains unexpectedly advanced. The climate of Crete makes this achievement even more impressive. Annual rainfall across central Crete averages roughly 500 to 800 millimeters, but precipitation often arrives through short, intense winter storms capable of producing large volumes of runoff within minutes. Large paved courtyards can rapidly become collection surfaces directing thousands of liters of water toward the drainage system. To prevent catastrophic flooding, engineers had to ensure that channels possessed sufficient carrying capacity while also controlling water velocity. Excavated drains reveal changes in width, depth, and direction that appear deliberately designed to moderate flow energy before water reached vulnerable structural areas. Certain sections widen into settling chambers where heavier sediment could naturally accumulate before cleaner water continued downstream. Whether these features were created through theoretical understanding or centuries of accumulated observation remains impossible to determine. Yet they demonstrate an intimate familiarity with the behavior of flowing water that exceeds what many historians once believed possible for Bronze Age engineering. Equally puzzling is the remarkable durability of the system. Underground stone channels survived repeated earthquakes that repeatedly damaged and reconstructed the palace itself. Crete lies near the active boundary between the African and Eurasian tectonic plates, making seismic activity a persistent threat throughout antiquity. Evidence suggests that major earthquakes contributed to the destruction of the original palace around 1700 BC, after which the complex was rebuilt while preserving much of its hydraulic philosophy. The survival of numerous drainage elements implies that the channels were not merely excavated trenches, but carefully engineered structures capable of resisting ground movement. Flexible construction joints, thick stone lining, and the strategic placement of conduits within stable geological layers may all have contributed, although no consensus exists regarding the exact engineering principles involved. Maintenance presents another mystery that has received increasing scholarly attention. Any gravity-fed drainage network eventually faces obstruction from mud, leaves, gravel, organic waste, and mineral deposits. Without periodic cleaning, even a perfectly designed system rapidly loses efficiency. Excavations at Phaistos reveal relatively clean conduits with accessible junctions and inspection points suggesting that maintenance was anticipated from the beginning. Yet no surviving Linear A inscription describes who maintained these drains, how often they were cleaned, or how hydraulic management was organized within Minoan society. A sophisticated drainage network cannot function for centuries without continuous human oversight, implying the existence of skilled specialists whose knowledge disappeared along with the civilization itself. Perhaps the most striking feature of Phaistos is its advanced use of gravity as a controlled hydraulic system. Water was carefully directed, slowed, and discharged using only natural slopes, turning elevation into usable energy without any mechanical tools. Nearly 4,000 years ago, the Minoans achieved a level of efficiency comparable to modern gravity-fed engineering, relying solely on stone construction and precise planning. This suggests they did not merely adapt to their environment but actively engineered it into a functional water management system. As a result, Phaistos is more than a palace. It is evidence of an early civilization with surprisingly sophisticated hydraulic knowledge. While the exact methods behind its design and calculations remain unknown. Priene water system, Western Turkey, an entire city where gravity became the machine. Perched on the southern slope of Mount Mycale overlooking the Meander Plain, the ancient Greek city of Priene transformed nothing more than elevation into a technology capable of supplying water to thousands of people without pumps, engines, or mechanical power. More than 23 centuries later, archaeologists still debate how its engineers achieved a level of hydraulic precision that appears remarkably sophisticated even by later standards. The hidden system emerged gradually through excavations that began in the late 19th century, especially the German investigations led by Theodor Wiegand after 1895. Beneath collapsed streets, houses, temples, fountains, and public buildings, archaeologists uncovered an extensive network of terracotta pipelines, carefully built stone channels, reservoirs, settling basins, distribution points, and drainage systems extending throughout the orthogonal city plan, first associated with the architect Hippodamus. Instead of isolated water installations, the discoveries revealed something far more ambitious: an integrated hydraulic network designed as part of the city's original construction during the 4th century BC. Every major structure appeared connected to a carefully calculated circulation system in which gravity alone provided the energy needed to move water from mountain springs toward every district below. That realization immediately raised a question that remains difficult to answer. Gravity is simple, but controlling gravity is not. Water naturally accelerates downhill. Pressure constantly changes with elevation, and every alteration in slope affects both velocity and structural stress. Modern hydraulic engineers solve these problems using mathematical models, pressure-reducing valves, reinforced joints, surge protection, and continuous monitoring. None of those technologies existed in classical Greece, yet Priene functioned for centuries with a network that distributed water across a densely planned urban landscape while maintaining reliable flow for domestic houses, fountains, baths, workshops, and religious sanctuaries. The city itself provided the first advantage. Built approximately 370 meters above sea level on a steep mountainside, Priene occupied a terrain that naturally created hydraulic head. Water collected from springs higher on Mount Mycale entered reservoirs before descending into the city through enclosed pipelines. Every meter of elevation generated additional potential energy, eliminating the need for lifting devices once the water entered the system. In modern engineering terms, the landscape itself became an enormous gravity-powered reservoir, converting altitude directly into usable hydraulic pressure. The concept sounds straightforward, yet transforming a rugged mountainside into a stable municipal water supply required extraordinary control over gradients that were never allowed to become either too steep or too shallow. Excavations indicate that engineers continuously adjusted channel inclinations as the network crossed streets and residential terraces. A channel descending too rapidly would increase turbulence, accelerate erosion, and generate damaging pressure fluctuations. A channel descending too slowly would encourage sediment accumulation, reduce flow velocity, and eventually clog the system. The remarkable consistency observed in surviving sections suggests careful surveying before construction even began. Archaeologists know the Greeks possessed leveling instruments such as the chorobates described centuries later by Vitruvius. Yet no surviving document explains exactly how Priene's builders maintained such precise elevation differences across an expanding city where every deviation could have affected dozens of downstream connections. Their practical understanding appears to have exceeded the written technical knowledge that survives today. Even more intriguing is the apparent balance of hydraulic pressure throughout the network. Water pressure increases by roughly 1 atmosphere for every 10 meters of vertical descent. Since Priene occupied a substantial elevation range, lower neighborhoods should theoretically have experienced significantly greater pressure than higher districts. Excessive pressure could crack terracotta pipes, separate joints, or produce destructive water hammer effects whenever flow conditions changed. Archaeologists have identified reservoirs and intermediate distribution structures that probably helped regulate these differences, while variations in pipe diameter may also have moderated velocity and pressure. Even so, the complete hydraulic logic remains uncertain because no mechanical pressure regulators have ever been discovered. The system appears to have achieved equilibrium almost entirely through geometry, elevation, and careful planning, rather than movable engineering devices. That leads directly to one of Priene's greatest mysteries. The city behaved less like a collection of independent pipelines and more like a single hydraulic organism. Public fountains required continuous flow. Houses demanded predictable supply. Religious buildings needed clean water for rituals. Excess water had to leave the city efficiently, without contaminating drinking sources. Every branch influenced every other branch. If one section consumed excessive water, neighboring districts should have experienced noticeable reductions in flow. Yet, archaeological evidence indicates the network remained functional through repeated phases of occupation. Many researchers suspect the engineers intentionally designed branching sequences, reservoir capacities, and pipeline dimensions so the entire system naturally balanced itself through gravity alone. If true, they effectively programmed hydraulic behavior into the physical landscape centuries before mathematics formally described many of the governing principles. Perhaps the most astonishing mystery concerns leakage. Terracotta pipelines appear deceptively simple, consisting of cylindrical sections generally between 40 and 70 centimeters long, connected end to end beneath streets and buildings. A citywide distribution network required thousands of individual joints. Every joint represented a potential failure point where escaping water could gradually undermine roads, weaken foundations, reduce pressure, or flood nearby structures. In modern buried pipeline systems, leakage control remains one of the greatest maintenance challenges, despite precision manufacturing and synthetic sealing materials. Yet many excavated sections at Preen still exhibit remarkably tight connections considering they remained buried for more than 2,000 years. Archaeologists have identified traces of lime-based mortars and sealing compounds in some locations, but the complete construction technique remains unknown. Questions persist about how individual pipe sections were aligned with sufficient accuracy, how thermal expansion was accommodated, how settlement of the underlying soil failed to separate countless joints, and how builders maintained watertight connections across an entire urban network exposed to seasonal temperature changes, earthquakes, and centuries of ground movement. No surviving technical manual explains the assembly process, leaving modern researchers to reconstruct methods only from the archaeological remains themselves. The durability of the system becomes even more remarkable when considering Western Anatolia's geological environment. The region lies within an active tectonic zone affected by repeated earthquakes throughout antiquity. Ground movement capable of shifting only a few centimeters could disrupt underground pipelines, alter carefully calculated gradients, or fracture ceramic conduits. Evidence shows that Preen underwent rebuilding after seismic events, yet substantial portions of its hydraulic infrastructure continued serving the city across generations. Whether this resilience resulted from flexible pipe joints, carefully prepared bedding materials beneath the conduits, or construction techniques now lost, remains uncertain. The surviving archaeological record demonstrates success without fully revealing the engineering decisions responsible for that success. The water system also reveals an impressive understanding of water quality. Before reaching public users, spring water frequently passed through settling installations where suspended sediments could accumulate before entering narrower distribution pipes. This reduced blockage while protecting fountains and household outlets from excessive debris. Engineers therefore addressed not only movement, but also purification through passive hydraulic design. Gravity simultaneously transported water, removed sediments, stabilized flow, and powered distribution without consuming fuel or requiring continuous human labor. Every natural process became part of the engineering itself, rather than an obstacle needing mechanical correction. Aphrodisias Fountain Complex in southwestern Turkey transformed gravity into an invisible machine long before engines existed. Hidden behind elegant marble architecture stood one of the most sophisticated hydraulic systems of the Roman world, where flowing water was not simply transported, but carefully controlled, balanced, divided, slowed, accelerated, and reused without a single mechanical pump. Much of that system survives only as buried channels, broken pipes, and scattered reservoirs, leaving archaeologists with an engineering puzzle whose most remarkable achievements are still only partially understood. The true complexity of the monument emerged gradually through archaeological excavations beginning in the early 20th century and expanding after systematic investigations led by New York University from the 1960s onward. Beneath collapsed marble blocks, researchers uncovered lead pipes, terracotta conduits, underground channels, settling basins, drainage passages, and the foundations of an enormous nymphaeum facing the city's main avenue. Rather than serving as an isolated ornamental fountain, every discovery revealed that the structure formed only one visible section of an integrated hydraulic network supplied from springs located in the surrounding hills. Water traveled several kilometers before entering the city, following gradients gentle enough to preserve continuous flow while preventing destructive erosion. Laser surveys conducted during modern conservation projects confirmed that even small variations in elevation could dramatically affect pressure throughout the network, demonstrating how dependent the entire system was upon exceptionally accurate control of gravity alone. That immediately raises the first unanswered question. Roman engineers possessed no pressure gauges, electronic levels, or mathematical models describing fluid dynamics in the modern sense. Yet the water reached Aphrodisias with enough force to feed monumental fountains, while remaining stable enough for daily public use. Hydraulic pressure depends entirely on differences in elevation, meaning every reservoir, channel, junction, and outlet had to occupy carefully chosen heights. A miscalculation of only a small amount across several kilometers could have reduced pressure until fountains barely flowed or increased velocity enough to damage masonry and pipes. Surveyors certainly relied upon instruments such as the chorobates and groma, but the precision preserved within surviving remains suggests a level of practical hydraulic knowledge far exceeding what surviving Roman technical texts describe, leaving researchers uncertain how much empirical experimentation, accumulated craftsmanship, or undocumented engineering tradition disappeared with the civilization itself. As excavation expanded beyond the monumental facade, the greatest mystery emerged from the distribution network hidden underneath the city. The fountain complex did not receive water simply to discharge it into one basin before allowing it to drain away. Instead, archaeological evidence indicates that incoming flow was divided into numerous branches feeding multiple fountains, pools, public buildings, and urban facilities distributed across different sectors of Aphrodisias. Modern hydraulic engineering predicts that water naturally favors the path offering the least resistance. Branches closest to the source normally receive greater discharge, while distant outlets experience progressively lower pressure unless the system is deliberately balanced. Yet measurements of surviving conduits suggest that many outlets across the complex operated with surprisingly consistent flow. This is perhaps the most astonishing aspect of the entire installation, because no mechanical valves or automated regulators have been found capable of continuously correcting pressure differences. Somehow, the network itself appears to have acted as the regulating mechanism. Researchers have proposed several explanations, although none completely accounts for the observed balance. The varying diameters of surviving lead pipes may have intentionally increased resistance within certain branches while reducing it in others, allowing discharge to equalize despite different distances from the source. Some conduits appear slightly narrower than expected, suggesting engineers deliberately sacrificed speed in one section to preserve pressure elsewhere. The lengths of individual pipelines may also have been carefully adjusted, so friction losses compensated for changes in elevation. Even the arrangement of junctions appears unusually deliberate, avoiding sharp turns that generate turbulence while favoring smoother transitions capable of maintaining stable flow. Modern computational models demonstrate that changing pipe diameter by only a few centimeters or altering elevation by tens of centimeters can significantly redistribute hydraulic pressure throughout an entire network. Whether Roman engineers calculated these relationships mathematically or perfected them through generations of observation, remains completely unknown. The surrounding reservoirs deepen the mystery even further. Excavated settling tanks positioned before parts of the distribution network almost certainly removed sediment carried from the aqueduct, protecting pipes from blockage, yet their dimensions suggest they performed additional hydraulic functions. Several researchers believe these reservoirs also acted as pressure buffers, absorbing fluctuations produced by seasonal variations in spring discharge before water entered the urban system. Such a mechanism would reduce sudden surges while maintaining nearly constant head pressure feeding the fountains. The principle resembles modern surge tanks installed in hydroelectric facilities and municipal water systems, although no surviving Roman document explicitly describes the concept in theoretical terms. Because large portions of the original plumbing disappeared through centuries of stone robbing and metal recycling, confirming this hypothesis remains exceptionally difficult. Seasonal change introduces another puzzle that has never been fully resolved. Spring supplying aphrodisias could not have delivered identical discharge throughout the year. Winter rainfall, prolonged drought, evaporation, and sediment accumulation continuously altered available flow, yet monumental fountains depended upon relatively stable performance to preserve both civic function and visual spectacle. If incoming discharge varied significantly, pressure across the city should also have fluctuated. Archaeologists therefore suspect additional overflow chambers or regulating basins once existed upstream, although many have either collapsed or remain buried beneath later deposits. Without those missing components, reconstructing the complete hydraulic sequence is impossible, leaving an important part of the system permanently hidden beneath the landscape. Equally remarkable is the way gravity continued working after water completed its decorative purpose. Overflow channels discovered beneath the fountain directed excess water towards secondary reservoirs, drainage conduits, and other urban installations, instead of allowing it to disappear immediately. Every change in elevation extracted another useful stage from the same water supply before the remaining flow ultimately entered the city's drainage network. This cascading sequence transformed height into usable energy repeatedly, illustrating that Roman engineers viewed gravity not as a passive natural force, but as an active technological resource capable of performing continuous work without fuel or mechanical assistance. In modern terminology, the entire city functioned as a gravity-powered hydraulic machine, whose energy source was simply the elevation difference between distant springs and the urban streets below. Earthquakes affecting Western Anatolia add one final unanswered question. Aphrodisias experienced repeated seismic activity throughout its history, damaging temples, public buildings, and monumental architecture. Hydraulic networks are especially vulnerable because even minor ground movement can fracture pipes or alter carefully maintained gradients. Excavation has revealed repairs made during different periods, proving the system remained operational long after significant earthquakes. Whether Roman engineers intentionally designed flexible joints, replaceable pipe sections, or maintenance strategies capable of restoring hydraulic balance after seismic disturbance remains uncertain because too much of the original plumbing has vanished. What survives instead is a fragmented network whose sophistication becomes clearer with every excavation, while its underlying design principles remain frustratingly incomplete. Dugga, northwestern Tunisia. Gravity became the only machine an entire city needed. Long before pumps, turbines, or pressure regulators existed, water crossed rugged hills, entered reservoirs perched above the streets, and supplied fountains, baths, temples, workshops, and homes through nothing more than carefully controlled elevation. The engineering itself is visible. The knowledge that made it possible has almost completely disappeared. The ruins of Dugga, ancient Thugger, remained remarkably well preserved because the Roman city was never buried beneath later urban development. Systematic archaeological excavation began during the 19th century after European expeditions documented the monumental remains and inscriptions scattered across the hillside. As excavations expanded throughout the 20th century, archaeologists uncovered extensive cisterns, aqueducts, distribution basins, fountains, and underground channels that revealed an urban hydraulic network serving one of the best preserved Roman cities in North Africa. Although many structures survive, the calculations behind their construction were never recorded. Modern engineers can trace where the water flowed, but not how Roman surveyors achieved such precision before construction even began. Everything starts with geography. Dugger occupies a steep limestone ridge approximately 600 meters above sea level, where streets climb and descend across irregular terrain instead of following a flat plain. Supplying water to such a settlement should have been considerably more difficult than supplying a city built beside a river. Yet Roman engineers transformed the landscape into a gravity-powered hydraulic machine. Springs located at higher elevations fed aqueducts that extended for many kilometers before reaching reservoirs positioned above the city. From there, gravitational potential energy alone maintained continuous water flow without mechanical pumps. This principle appears simple today, yet applying it successfully across an uneven landscape required extraordinary control over elevation differences measured across thousands of meters. Even a relatively small surveying error could interrupt the entire network, causing water either to stagnate or accelerate beyond safe limits. That immediately raises the greatest unanswered question surrounding Dugger. How did Roman engineers maintain an almost continuous hydraulic gradient across such irregular terrain without modern surveying equipment? The route crossed natural ridges, shallow valleys, fractured limestone, unstable soil, and changing bedrock elevations, yet archaeological studies indicate that the channels maintained gradients gentle enough to preserve steady flow while avoiding destructive velocities. Modern hydraulic engineering solves this challenge using laser levels, satellite positioning, electronic total stations, and digital terrain models capable of measuring elevation differences within millimeters. Roman surveyors possessed none of these technologies. Historical sources mention instruments such as the chorobates, the groma, measuring rods, plumb lines, and water levels, yet many engineers question whether these tools alone could repeatedly achieve the precision implied by surviving aqueduct systems. A channel descending too rapidly would erode masonry, increase turbulence, and damage joints. A channel descending too slowly would encourage sediment accumulation until the flow gradually stopped. The remarkable consistency observed across many Roman hydraulic systems suggests careful planning before construction began, but no surviving engineering manual explains how surveyors converted a rugged natural landscape into a stable hydraulic profile. The physical infrastructure survives, while the mathematical process used to design it has vanished almost entirely. As the water finally entered Dugger itself, gravity continued performing tasks that modern cities usually assign to mechanical equipment. Reservoirs constructed at different elevations acted as hydraulic buffers, reducing pressure fluctuations before water entered secondary distribution channels. Instead of relying upon powered valves or pressure-regulating machinery, the entire network exploited differences in height. Every meter of elevation represented stored energy waiting to be released in a controlled manner. Public fountains required constant discharge, baths demanded significantly larger volumes, while domestic users consumed water at lower and more variable rates. Balancing these competing demands without pumps required exceptional understanding of hydraulic behavior. Archaeologists have reconstructed portions of the distribution network, yet many branches remain incomplete because later stone removal destroyed important sections. Consequently, researchers still debate exactly how water was divided between public monuments, neighborhoods, and industrial facilities. Whether specialized regulating devices existed, or whether the entire system depended almost exclusively upon elevation differences, remains uncertain. The condition of several surviving hydraulic structures introduces another puzzle. Ancient water systems commonly suffer from thick deposits of calcium carbonate that gradually reduce channel capacity. Sediment accumulation also slows flow, eventually requiring expensive maintenance. Evidence from Dugger indicates that although mineral deposits certainly formed, large sections continued operating effectively for centuries despite continuous exposure to hard water. One explanation proposes that Roman engineers intentionally selected gradients capable of maintaining self-cleansing velocities, allowing flowing water to transport suspended particles before significant blockages developed. Similar hydraulic principles are used in modern sewer engineering, where minimum flow velocity prevents sediment from settling. Yet proving that Roman engineers intentionally calculated such behavior remains extremely difficult because no written documentation survives describing their design criteria. The physical evidence demonstrates successful long-term performance, but it cannot reveal whether those results emerged from mathematical prediction, accumulated practical experience, or generations of empirical experimentation refined through repeated construction. Another remarkable feature becomes visible only when the entire city is examined, rather than individual monuments. Dugger was not supplied by isolated pipes, serving disconnected buildings. Instead, reservoirs, aqueducts, settling basins, fountains, baths, drainage channels, and underground conduits formed a single integrated hydraulic organism. Water entered at the highest practical point, gradually released its stored gravitational energy while serving multiple functions, and eventually exited through drainage systems positioned at lower elevations. Gravity transported clean water, stabilized pressure, distributed supply, powered continuous flow, and removed wastewater without reversing direction or requiring external energy. Every component depended upon the precise elevation of every other component. Altering only one major level could potentially disrupt the balance of the entire network. Such interdependence required city planning that extended far beyond individual buildings and suggests that hydraulic design influenced urban development from the earliest construction phases. The absence of detailed technical records deepens the mystery. Roman civilization left extensive legal documents, military histories, architectural treatises, and inscriptions celebrating emperors, yet almost nothing explains the field procedures that allowed surveyors to establish stable hydraulic gradients across landscapes as complicated as Dugger. Vitruvius described certain surveying methods, but his writings remain too general to reconstruct the exact workflow used on challenging terrain. No preserved notebook records daily elevation measurements. No construction diagrams identify reference benchmarks. No surviving inscription describes how workers repeatedly transferred accurate levels over several kilometers before laying the first stone. Modern archaeology therefore reconstructs the finished machine, while remaining largely unable to reconstruct the sequence of calculations that created it. Pergamon Acropolis in western Turkey transformed gravity into one of the most powerful machines of the ancient world. Rising more than 330 meters above the surrounding plain, this Hellenistic capital appears almost impossible as a place for abundant fresh water. Yet archaeological excavations beginning in the late 19th century uncovered aqueducts, reservoirs, pressure pipelines, and the remains of one of antiquity's most remarkable hydraulic systems. Instead of relying on pumps, wheels, or mechanical engines, the engineers of Pergamon designed an entire network in which differences in elevation alone generated the energy needed to move water across more than 40 kilometers of rugged terrain. Long before the science of fluid mechanics was formally understood, they had already learned how to make gravity perform work on a scale that still impresses hydraulic engineers. As researchers reconstructed the surviving channels and measured their elevations, they realized that the greatest challenge was not carrying water toward the city, but bringing it across a deep valley immediately before reaching the Acropolis. An ordinary open aqueduct would have failed, because once water descended into the valley, it could never climb back to the fortress on the opposite side. The solution was astonishingly sophisticated. Instead of keeping the water exposed, the builders enclosed it inside lead pipes that descended the valley, crossed its lowest point, and then rose toward the city in what modern engineers describe as an inverted siphon. The principle appears simple today. Water falling through a vertical difference of nearly 190 meters created enormous hydrostatic pressure inside the sealed pipeline, and that stored pressure forced the water upward until it nearly reached the same elevation from which it had originally descended. Gravity itself became the engine, continuously converting height into pressure without consuming fuel or requiring moving parts. Every drop of water entering the system effectively carried its own source of energy. That elegant concept immediately raises the greatest mystery surrounding Pergamon, because calculations based on modern physics indicate that a vertical water column approaching 190 meters would generate pressures close to 19 or even 20 bar, roughly 20 times normal atmospheric pressure, or nearly 290 pounds per square inch. Such pressure is common inside modern industrial pipelines manufactured from steel, yet Pergamon relied primarily on lead. Lead is relatively soft, easily deformed, and far weaker than modern alloys, making the survival of this hydraulic network one of the most puzzling engineering achievements of the ancient Mediterranean. Archaeologists have recovered sections of the pressure pipes, together with connectors and fittings, confirming that lead was indeed used where the highest pressures occurred, but no surviving construction manual explains how those pipes consistently resisted forces that should have split weak joints apart or gradually expanded the metal until catastrophic failure occurred. The mystery becomes even deeper because the system reportedly remained operational for generations rather than only a brief experimental period. Every year of successful operation meant that thousands of pressure cycles passed through the same network without destroying it. Several explanations have been proposed, yet none fully resolves the question. Some engineers believe the lead pipes were manufactured with walls considerably thicker than previously assumed, sacrificing material efficiency for structural safety. Others suggest the builders deliberately limited internal stress by carefully selecting pipe diameters, allowing pressure and flow velocity to remain within acceptable limits. Another possibility is that the joints between individual pipe sections were reinforced with bronze collars, stone supports, or specially cast sleeves that distributed mechanical loads more evenly than modern reconstructions usually assume. Even so, these theories remain incomplete because only fragments of the original pipeline survive, leaving many critical construction details permanently lost. What survives instead is the undeniable physical evidence that the system functioned despite operating under pressures that many historians once believed impossible for Hellenistic technology. The more investigators study Pergamon, the more another question emerges. High pressure alone cannot explain the success of the network, because pressure is only one variable in a much larger hydraulic equation. The engineers also had to calculate gradients over dozens of kilometers, estimate friction losses inside the pipes, prevent trapped air from interrupting flow, and ensure that enough pressure remained after crossing the valley to deliver water into reservoirs at the summit. Modern engineers perform these calculations using mathematical formulas, surveying instruments, and computer simulations, yet the builders of Pergamon possessed none of these tools in their present form. They had no pressure gauges, no differential equations, and no modern theory describing hydraulic head. Yet the completed system behaves as though every one of those variables had already been accounted for. Whether those results emerged from generations of experimentation, extraordinary practical geometry, or empirical rules that have since disappeared, remains uncertain. Equally mysterious is the remarkable accuracy with which the route itself was surveyed. The water traveled across mountains, ridges, and valleys before finally reaching the Acropolis, meaning even modest surveying errors could have caused air pockets, excessive turbulence, or complete hydraulic failure. The alignment instead demonstrates an exceptional understanding of landscape. Reservoirs were positioned where they could stabilize supply, channels maintained carefully controlled gradients, and the pressure pipeline occupied exactly the portion of terrain where gravity could be transformed into usable hydraulic energy. Every component appears integrated into a single design philosophy, rather than assembled through trial and error, suggesting that the planners understood the behavior of flowing water at a systems level rarely associated with the 3rd or 2nd century BCE. Researchers have also wondered how the network survived natural hazards for so long. Western Anatolia lies within an active seismic region where earthquakes repeatedly disturb foundations and fracture masonry. Seasonal temperature changes expand and contract metal, while flowing water gradually wears away pipe interiors and weakens joints through corrosion. Modern pressure pipelines often require continual inspection, replacement, and maintenance under comparable conditions. Yet the archaeological evidence indicates that Pergamon's hydraulic infrastructure remained reliable enough to sustain one of the wealthiest cities of the Hellenistic world. Such durability implies that maintenance procedures may have been as sophisticated as the engineering itself, although almost nothing describing those procedures has survived in written sources. The decision to construct extensive sections of the system from lead introduces another unresolved puzzle, because lead represented an expensive material requiring specialized extraction, smelting, transport, and casting. Clay pipes would have been cheaper, but brittle ceramic could not tolerate the immense internal pressures generated by the inverted siphon. Stone channels excelled, where water flowed under atmospheric conditions, but became impractical once pressure vessels were required. The builders therefore selected the only material flexible enough to create sealed pipelines while still resisting substantial stress, revealing an advanced understanding of material properties, even if they could not explain those properties scientifically. Their choice demonstrates that the project was guided by engineering necessity rather than economy, indicating that securing a dependable water supply for the elevated capital outweighed enormous construction costs. On Spain's southeastern Mediterranean coast, near the mouth of the Segura River, lies La Fonteta, an ancient Phoenician settlement buried beneath sand and silence. Nearly 3,000 years ago, it was one of the most important gateways between the Mediterranean world and the Iberian Peninsula. Today, the city remains, but its harbour, the very reason for its existence, has seemingly vanished from history. Archaeological excavations conducted during the late 20th century revealed the remains of a fortified Phoenician settlement dating between the 8th and 6th centuries BCE. Beneath layers of dunes, researchers uncovered massive defensive walls, industrial zones, imported luxury goods, and evidence of extensive maritime trade. Yet the most important structure expected at such a site, a major harbour, remains elusive. At first glance, La Fonteta appears far less impressive than famous sites such as Machu Picchu, Petra or Baalbek. There are no colossal temples, giant statues, or megalithic blocks weighing hundreds of tons. Yet beneath its modest appearance lies a different kind of mystery, evidence of sophisticated engineering knowledge that seems unexpectedly advanced for its age. The settlement occupied a highly challenging environment near a river delta. Modern civil engineers recognize such landscapes as difficult locations for permanent construction. River mouths experience constant sediment deposition, flooding, shoreline migration, groundwater fluctuations, and soil instability. Even with modern surveying equipment, constructing durable infrastructure in such environments requires careful planning. Yet Phoenician builders established a thriving urban centre here nearly 3,000 years ago. The city's defensive walls reached thicknesses estimated between 4 and 5 meters. Excavations revealed reinforcement systems and regularly spaced structural supports that appear designed to distribute stress and prevent large-scale collapse. Some researchers have suggested these features may have improved resistance against seismic activity or foundation movement. The intriguing question is not whether the walls worked. They clearly did. The mystery is how engineers of the 8th century BCE acquired enough practical understanding of structural behavior to implement solutions that resemble concepts used in modern engineering. No surviving technical manuals explain their methods, and no architectural blueprints have been discovered. The knowledge itself seems to have vanished while the walls remained. The greatest puzzle surrounding La Fonteta concerns something that should have been impossible to lose: an ancient harbour. Historical and archaeological evidence strongly suggests that La Fonteta functioned as a major maritime trading centre. Imported materials found at the site include Greek pottery, Egyptian-style scarabs, ivory objects, luxury ceramics, and goods originating from regions hundreds or even thousands of kilometres away. Such trade networks do not emerge without maritime infrastructure. Ships needed protected docking areas, cargo required loading facilities, merchants needed warehouses, and navigation demanded channels deep enough for vessels. A functioning harbour should have existed, yet archaeologists cannot fully locate it. This is one of the most fascinating enigmas in Mediterranean archaeology. 3,000 years ago, the shoreline stood dramatically closer to the settlement than it does today. Geological studies indicate that sediment carried by the Segura River gradually transformed the landscape. Coastal processes deposited enormous quantities of sand and silt over centuries. What was once open water became marshland, dunes, and agricultural terrain. In effect, nature rewrote the map. Modern satellite imagery reveals little resemblance to the ancient coastline. The harbour that sustained La Fonteta may now lie buried beneath meters of sediment, hidden beneath modern terrain, or destroyed by centuries of environmental change. The scale of this transformation is difficult to visualize. Consider the ancient harbour of Ephesus in modern Turkey. Once located directly on the coast, it now lies several kilometers inland because of river sediment accumulation. Similar processes altered the landscape around Miletus, Ostia, and numerous other ancient ports throughout the Mediterranean. La Fonteta may represent an even more extreme case. Archaeologists know the city depended on maritime trade. They know ships arrived here, and they know goods flowed through the settlement. Yet the infrastructure enabling that activity remains largely invisible. It is a port city without a visible port, a maritime centre whose harbour has disappeared. Few archaeological mysteries illustrate the power of geological change so dramatically. The harbour mystery raises another question. How did Phoenician engineers understand coastal dynamics well enough to establish a successful port in the first place? Modern harbour construction requires analysis of sediment transport, currents, wave energy, seasonal flooding and shoreline stability. Engineers use mathematical models, satellite observations and decades of environmental data. Phoenician builders possessed none of these tools, yet their trading network stretched across more than 3,000 kilometres of coastline, connecting the Levant with North Africa, Sardinia, Sicily, southern Spain and beyond. The success of this network suggests practical expertise accumulated over generations. La Fonteta may represent evidence of an engineering tradition based not on written science but on centuries of observation and experience. The problem is that archaeology can observe the results of that knowledge but struggles to reconstruct the intellectual processes behind it. The harbour may be gone, but the sophistication required to create it remains visible in the city's existence. Excavations have revealed evidence of metallurgical activity within the settlement. This discovery transformed scholarly understanding of La Fonteta. For many years, researchers viewed Phoenician colonies primarily as commercial outposts. Increasing evidence now suggests that some functioned as manufacturing centres as well. Metalworking debris, furnaces and industrial remains indicate local production activities. The implications are significant. Iron technology was spreading across the Mediterranean during this period. Mastery of smelting and metal processing required precise temperature control, fuel management, ore selection, and specialized knowledge accumulated through experimentation. Experimental archaeology demonstrates that producing high-quality iron consistently is remarkably difficult, even when modern researchers attempt to replicate ancient methods. Tiny variations in furnace temperature can drastically affect results, impurities can ruin an entire production cycle, and airflow must be carefully controlled. Yet ancient metallurgists achieved results sufficient to support expanding regional economies. At La Fonteta, the full technological system remains only partially understood. Researchers have identified evidence of production, but they have not fully reconstructed the process. The technology exists in fragments, and the knowledge that created it remains incomplete. The artifacts discovered at La Fonteta tell a remarkable story. Objects originating from distant cultures arrived at this relatively small settlement on the edge of the Iberian Peninsula. Such findings reveal an interconnected world centuries before the rise of Rome. Comparisons with modern trade networks are tempting. Although ancient commerce operated on a vastly smaller scale, the underlying principle was similar. Specialized regions exchanged resources, technology, luxury goods, and information across enormous distances. The challenge lies in understanding navigation. Phoenician sailors crossed open waters without compasses, GPS, radar, or accurate longitude calculations. Ancient sources suggest they navigated using stars, prevailing winds, coastal landmarks, and accumulated experience. Yet historians continue debating how precise these methods truly were. The repeated success of long-distance voyages suggests a level of maritime expertise that remains difficult to quantify. Once again, the achievements are visible, while the underlying techniques remain partially hidden. What do you think happened to La Fonteta's lost harbour? Was it buried by nature, destroyed by disaster, or is it still waiting to be discovered beneath the sands? Share your thoughts in the comments below. On a rocky promontory overlooking the Tyrrhenian Sea in western Italy lies Populonia ***, the only major Etruscan city built directly on the coast. Today it appears as a quiet archaeological site, but more than 2,000 years ago it may have been one of the largest iron processing centres in the ancient world, a place where millions of tons of ore were transformed into metal using technologies that archaeologists still struggle to fully reconstruct. Unlike many lost cities hidden beneath jungle or desert, Populonia was never completely forgotten, yet its greatest secret remained unnoticed for centuries. Massive hills surrounding the site were long assumed to be natural formations, until modern archaeological investigations reveal that many of them were actually gigantic accumulations of iron-smelting waste. Beneath these seemingly ordinary mounds lay evidence of an industrial landscape unlike anything previously associated with the Etruscans. Most ancient cities are remembered for temples, palaces, or defensive walls, but Populonia is different because its true monument is waste. Archaeologists estimate that the region once contained millions of tons of metallurgical slag, the byproduct of iron production, with some deposits reaching several meters in depth and covering extensive portions of the coastline. The sheer scale suggests industrial activity operating continuously across centuries, creating an immediate paradox. The Etruscans are often portrayed as a sophisticated but relatively small civilization that flourished before Roman domination. Yet the volume of material processed at Populonia appears closer to what one might expect from a major industrial center than from a modest ancient city. The source of this wealth lay across the water on the island of Elba, whose iron deposits rank among the richest in Europe, and ancient ships transported ore from the island to Populonia, where it was smelted, refined, and distributed throughout the Mediterranean. The basic process is understood, but the scale is not. Among all the mysteries surrounding Populonia, none may be more fascinating than the performance of its iron industry. Extracting iron from ore is not a simple task, as the process requires temperatures often exceeding 1,100 degrees Celsius, making it difficult not only to achieve such heat, but even harder to maintain it consistently. Modern metallurgical operations rely upon precise temperature monitoring, controlled airflow, and extensive understanding of chemical reactions. Yet the Etruscans possessed none of these advantages. They had no thermometers, no modern furnaces, no steel refractory materials, and no chemical laboratories. Despite this, analyses of ancient slag indicate surprisingly efficient extraction rates, with remaining waste often containing less recoverable iron than researchers would expect from primitive smelting systems, suggesting that Populonia's metallurgists were remarkably successful at extracting metal from ore. How they achieved this remains controversial. Experimental archaeologists have attempted to recreate Etruscan furnaces using traditional materials, and while some experiments successfully produced iron, they often required extensive experience and repeated adjustments, making it difficult to reproduce ancient efficiency even under controlled modern conditions. The challenge becomes even more striking when compared with other ancient societies, many of which lost significant quantities of metal within slag deposits due to difficulties in controlling furnace chemistry. At Populonia, however, evidence suggests operators frequently approached levels of performance that appear unexpectedly advanced for the period. Some researchers propose that generations of practical experimentation allowed Etruscan craftsmen to develop highly refined empirical knowledge, while others argue that furnace designs themselves may have incorporated innovation still poorly understood because so few complete examples survive. The result is a rare archaeological mystery. We possess the waste, we know the outcome, yet the precise methods remain largely invisible. One of the greatest frustrations for archaeologists is that the enormous slag fields survived far better than the facilities that produced them, as millions of tons of waste remain while most furnaces do not. The structures responsible for this industrial output were built largely from materials vulnerable to erosion, recycling, and destruction over centuries, forcing researchers to reconstruct entire technological systems from fragments. It is like discovering the tailings of a modern mining operation thousands of years in the future while finding only a few pieces of machinery, which is essentially the situation at Populonia. Because the physical evidence is incomplete, several competing theories exist. Some scholars suggest that furnace placement exploited coastal winds to intensify combustion naturally, while others propose sophisticated bellows systems capable of generating airflow far greater than traditionally assumed. Neither explanation fully resolves the problem, and the more researchers calculate the energy requirements of large-scale iron production, the more impressive the engineering becomes. The slag mountains themselves raise additional questions, as industrial waste is often imagined as chaotic accumulation, yet Populonia does not always fit that model. Archaeological surveys indicate patterns suggesting deliberate organization, management, and long-term planning, with waste concentrated in designated areas rather than randomly scattered across the landscape. This implies administration, meaning someone had to coordinate deliveries of ore, manage fuel supplies, organize labor, and maintain production schedules. Although the existence of such logistical systems is rarely visible in the archaeological record, the scale of activity suggests they must have existed, and in effect, Populonia may have functioned less like a traditional city and more like a highly integrated industrial complex. Iron production consumes enormous amounts of fuel, introducing another mystery. Every furnace required charcoal, charcoal required wood, and wood required forests, and modern calculations suggest that sustained metallurgical activity on the scale observed at Populonia would have consumed vast quantities of timber over centuries. This raises critical questions. Where did all that fuel originate? How were forest resources managed? And why did complete ecological collapse apparently not occur immediately? Comparable questions arise at other ancient industrial centres, such as Roman mining districts in Spain that transformed landscapes through large-scale extraction, or ancient copper production in Cyprus that required extensive fuel consumption. Yet Populonia appears to have maintained iron production for generations, while remaining economically viable. Some researchers suspect that extensive woodland management programs existed, while others believe fuel was imported from broader regions than traditionally assumed, though direct evidence remains limited. Another overlooked mystery involves transportation. As ore travelled from Elba to Populonia, fuel travelled from inland forests, and finished metal travelled across Mediterranean trade networks, with each stage requiring coordination. Ancient ships lacked engines. Ports lacked cranes powered by machinery, and navigation depended on environmental conditions, yet the system worked not occasionally but repeatedly for centuries. The comparison with later civilizations is revealing, as the Roman Empire developed vast transportation networks supported by roads, ports, and administrative infrastructure, while Populonia achieved large-scale industrial activity before Rome reached its greatest power. This raises an important possibility that the organizational capabilities of the Etruscans may have been significantly more sophisticated than traditionally acknowledged. If the Etruscans could achieve such remarkable iron production efficiency with the tools available to them more than 2 millennia ago, what crucial piece of knowledge do you think has been lost to history? Share your thoughts in the comments below. Royal Kurgan is a massive burial mound standing near Kerch on the eastern edge of Crimea, overlooking the narrow strait that links the Black Sea and the Sea of Azov. From the outside, it appears deceptively simple, a low hill of stone and earth rising above the landscape. Yet hidden within this mound is one of the most remarkable engineering achievements of the ancient Bosporan kingdom. More than 2,300 years after its construction in the 4th century BCE, Archaeologists are still debating how its builders achieved such extraordinary structural precision, using only the tools available in the classical age. Unlike many ancient mysteries associated with legends or lost civilizations, the mystery of Royal Kurgan is rooted in architecture, mathematics, and engineering knowledge that seems far ahead of what historians can confidently reconstruct. The monument became known to modern scholars during 19th century archaeological investigations of the Kerch Peninsula, a region rich in Greek and Bosporan remains. When excavators entered the mound, they expected a typical elite tomb. Instead, they discovered an astonishing stone passage leading toward a towering burial chamber, whose geometry immediately attracted attention. Although the tomb had been looted in antiquity, and much of its original funerary wealth had disappeared, the structure itself survived. Over time, researchers realized that the greatest treasure of Royal Kurgan was not what had been buried inside, but the engineering knowledge embedded within its stones. The most extraordinary feature is the gigantic corbel-vaulted burial chamber. The chamber rises to approximately 8.7 meters in height, equivalent to a modern 3-story building. At first glance, it resembles a true dome. Yet, it is not a dome in the Roman sense. No keystone locks the structure together. Instead, each successive ring of stone projects slightly inward over the layer below it until the opening narrows near the top. This technique, known as corbelling, was used in several ancient cultures, but Royal Kurgan represents one of the most sophisticated examples ever constructed around the Black Sea. The challenge becomes clear when engineers analyze the forces involved. Every stone must transfer its load downward while maintaining equilibrium. If even a small number of blocks were misaligned, the entire chamber could gradually deform and eventually collapse. Yet after more than 23 centuries, the structure remains standing. The obvious comparison is with the famous Tholos tombs of Mycenaean Greece, especially the treasury of Atreus, built around 1250 BCE. That monument reaches approximately 13.5 meters in height and was long regarded as one of the greatest corbel structures in the ancient world. Royal Kurgan is smaller, but its proportions are exceptionally elegant and precise. Researchers studying the geometry of the chamber have noted that the reduction in diameter toward the top appears highly systematic rather than improvised. The builders seem to have followed a carefully planned mathematical design. This raises an uncomfortable question. How did engineers of the Bosporan Kingdom calculate the stability of such a structure without modern structural mechanics, finite element analysis, or even formalized engineering equations? Ancient builders clearly understood the practical behavior of stone, yet the methods they used to predict long-term stability remain almost entirely undocumented. The mystery becomes even deeper when examining the stone blocks themselves. Many weigh several tons. Their surfaces show evidence of deliberate shaping and careful fitting. Modern measurements reveal surprisingly small gaps between adjacent blocks in critical areas of the chamber. While stone-cutting technology certainly existed throughout the Greek world, maintaining such consistency across an entire monument required remarkable quality control. Experimental archaeology demonstrates that workers using iron chisels and hammers can shape limestone with considerable precision. However, replicating the exact tolerances observed throughout Royal Kurgan would demand not only skilled craftsmen, but also standardized measuring systems. No surviving Bosporan engineering manuals explain how this level of accuracy was achieved. The entrance corridor introduces another layer of mystery. The dromos, or passageway, extends roughly 36 meters toward the burial chamber. Visitors often report a strange visual sensation as they move through it. The chamber appears larger than expected. While the proportions of the corridor seem subtly altered, architectural historians have suggested that the builders intentionally manipulated perspective. Similar optical refinements are known from classical Greek architecture. The Parthenon in Athens famously incorporates slight curvature in supposedly straight lines because the human eye perceives perfect geometry imperfectly. If Royal Kurgan employs related principles, its architects possess not only engineering expertise, but also an advanced understanding of visual psychology. Such sophistication would place the monument among the most intellectually ambitious structures of the Hellenistic world. Transportation presents another unresolved puzzle. Constructing the monument required thousands of tons of limestone. Every block had to be quarried, shaped, transported, lifted, and positioned with precision. Ancient engineers likely relied on sledges, rollers, ramps, ropes, wooden cranes, and large labor forces. Yet the exact methods remain speculative because no direct construction records survive. Modern engineers attempting to model the logistics estimate that the project would have required extensive planning and coordination. Even a small error in sequencing could have delayed construction or destabilized the partially completed chamber. The absence of written documentation means that the organizational systems behind the project remain invisible. We see the final result, but not the process that produced it. Perhaps even more impressive is the monument's long-term structural durability. Crimea lies within a region affected by seismic activity and significant seasonal temperature fluctuations. Over centuries, countless ancient buildings across Eurasia suffered severe damage from earthquakes, settlement, weathering, or human intervention. Royal Kurgan, however, has survived remarkably well. Some researchers believe the mound itself played a crucial engineering role. Rather than serving merely as a symbolic covering, the surrounding earth may have acted as a stabilizing shell, distributing pressure around the stone chamber and reducing structural stress concentrations. In modern engineering terms, the monument functions as a composite system in which stone and earth work together. Whether the builders consciously understood these principles or arrived at them through accumulated empirical experience remains uncertain. The geometry of the burial chamber has generated particular interest among structural analysts. Computer simulations suggest that corbel structures can remain stable for millennia when the center of mass of each successive layer remains within carefully defined limits. Yet achieving this balance requires remarkable precision. Ancient builders obviously lacked computer models, but they somehow developed construction methods that produced nearly identical outcomes. Similar mysteries appear at sites such as the Treasury of Atreus, Newgrange in Ireland, and certain neuralgic structures in Sardinia. Across vast distances and different cultures, ancient engineers repeatedly created stable stone chambers whose underlying design principles are only partially understood today. Royal Kurgan stands as one of the clearest examples of this phenomenon. Another unresolved question concerns the transfer of knowledge. The Bosporan kingdom existed at the crossroads of Greek, Scythian, and local traditions. Royal Kurgan combines elements from multiple cultural influences, yet the exact origin of its engineering concepts remains debated. Did its builders inherit techniques from earlier Greek architects? Were local craftsmen responsible for innovations adapted to regional conditions? Or did the monument represent the culmination of generations of experimentation now lost to history? The absence of surviving plans, calculations, and technical texts leaves these questions unanswered. What do you think is the most impressive mystery of Royal Kurgan? Was it the giant corbel vault, the remarkable precision of its stonework, or the lost engineering knowledge behind its construction? Share your thoughts in the comments below. In the volcanic valleys of southern Tuscany, Italy, lies Savana, a place where ancient engineers cut roads directly into solid rock so deeply and so precisely that even modern archaeologists still debate how they achieved it more than 2,000 years ago. Although the settlement itself was known throughout history, systematic archaeological investigation accelerated during the 19th and 20th centuries when researchers began documenting the vast Etruscan necropolis surrounding Savannah. What initially appeared to be a collection of tombs soon revealed something far more extraordinary: an immense network of sunken roads, monumental rock-cut architecture, and engineering works carved directly into volcanic stone. What archaeologists discovered was not merely a cemetery, it was an engineered landscape. The ancient Etruscans flourished in central Italy between roughly the 8th and 3rd centuries BCE, long before Rome became the dominant power of the Mediterranean. Many ancient civilizations built monuments. The Egyptians built pyramids, the Greeks built temples, and the Romans built aqueducts. The Etruscans at Savannah appear to have done something different. Rather than placing structures onto the landscape, they transformed the landscape itself. Across the valleys surrounding Savannah, researchers have identified numerous rock-cut tombs connected by an extensive system of excavated corridors known as V-cave. These passageways were not simply carved into existing cracks or ravines. In many locations, they were deliberately excavated through solid volcanic tuff, creating vertical walls that rise 10 to 20 meters above the pathways below. Standing inside one of these corridors feels less like walking through a road and more like moving through a gigantic artificial canyon. The scale alone raises questions. Thousands of cubic meters of stone had to be removed, every wall had to remain stable, every route had to maintain usable gradients, and all of this was accomplished without explosives, steel tools, engines, cranes, or modern surveying equipment. Among all the unanswered questions surrounding Savannah, perhaps none is more fascinating than the apparent sophistication of Etruscan surveying. Modern engineers understand how difficult it is to establish long, consistent alignments across uneven terrain, and today we rely on total stations, GPS receivers, laser scanners, satellite imagery, and digital terrain models. The builders of Savannah possessed none of these technologies, yet many V-cave display remarkable directional consistency. Researchers studying Etruscan landscapes have noted that these routes frequently maintain logical connections between settlements, agricultural zones, sacred areas, and necropolises, appearing integrated into a larger regional plan rather than being created randomly over time. This creates a difficult question. How did Etruscan engineers determine where to excavate? To carve a corridor through solid rock, surveyors must first establish a route, estimating elevation changes, drainage behavior, geological stability, and future usability, where any major error could multiply into thousands of hours of wasted labor. Even a deviation of a few degrees could dramatically alter the final path, yet many of these corridors follow terrain with impressive efficiency. Some researchers suggest that the Etruscans employed sophisticated geometric surveying methods using ropes, sighting poles, plumb lines, and astronomical observations, while others believe generations of accumulated practical experience allowed them to achieve surprising accuracy. The problem is that no surviving technical manuals explain their procedures. The roads survive, but the calculations do not. The engineering challenge becomes even more impressive when considering the sheer amount of material removed. A typical V-cave may extend hundreds of meters while reaching heights of 10 to 20 meters, and even conservative estimates suggest that many thousands of tons of rock were excavated. For comparison, modern construction projects involving comparable volumes would normally employ hydraulic excavators, drilling equipment, dump trucks, and laser-guided surveying systems. The Etruscans relied primarily on human labor. Archaeologists have identified tool marks on various rock surfaces, demonstrating systematic excavation techniques, yet the exact organization of labor remains unclear. Questions persist. How many workers participated? How long did individual corridors require? How was debris removed from narrow excavation zones? And where was the excavated stone deposited? Surprisingly, answers remain incomplete. The physical evidence proves the work occurred, but the logistics remain elusive. The volcanic tuff underlying savanna is relatively soft when freshly exposed, but becomes more durable after weathering, a property that undoubtedly aided excavation. However, it does not fully explain the survival of the corridors. Many walls remain standing after more than 2 millennia, suggesting that the builders understood far more about geology than is often assumed. When modern engineers cut into slopes, they analyze fracture systems, water infiltration, slope stability, load distribution, and erosion potential, as mistakes can trigger collapses. The Etruscans apparently achieved large-scale excavations while avoiding catastrophic structural failures across much of the landscape. This raises an intriguing possibility. Perhaps ancient builders possessed extensive empirical geological knowledge acquired through generations of quarrying, mining, and construction. They may not have possessed geological science in the modern sense, but they may have understood the behavior of local rock formations with extraordinary practical precision, and the surviving corridors themselves may be evidence of that expertise. One of the most overlooked mysteries of Savanna involves water. At first glance, the V-cave appear vulnerable. Deep trenches should collect rainfall, standing water should accelerate erosion, and seasonal flooding should damage the corridors. Yet many remain surprisingly stable. Researchers have identified drainage features integrated into various sections of the landscape, where subtle gradients encourage runoff and natural channels appear incorporated into broader designs. In some locations, erosion seems far less severe than expected given the age of the structures. The situation resembles challenges encountered at sites such as Machu Picchu, Petra, and the underground cities of Cappadocia, where water management appears inseparable from architectural survival. Without effective drainage, none of these sites should have endured for centuries. Savanna belongs within this same category of ancient engineering puzzles, and its builders seem to have understood hydrology well enough to protect massive, excavated features across extremely long periods of time. The tombs of Savanna introduce another layer of complexity. The most famous example, the tomb of Ildebranda, resembles a classical temple emerging from a hillside. What makes this structure remarkable is the method of construction. The builders did not assemble columns and walls from separate blocks, but instead removed the surrounding rock, meaning everything visible today was created by subtraction. Columns, stairways, chambers, decorative elements, and architectural facades were all carved from a single geological mass. This process required extraordinary planning, as a mason assembling blocks can replace damaged components, but a rock-cut architect cannot, and one major mistake can destroy years of work. Similar challenges appear at Petra in Jordan, the rock-cut churches of Lalibela in Ethiopia, and India's Kailasa temple. Yet Savanna remains distinctive because such techniques were applied across an entire funerary landscape rather than a single isolated monument. What do you think was the true purpose of the giant V-cave corridors of Savanna? Transportation, ritual processions, astronomical design, or something we still haven't discovered? Share your theory in the comments below. Near Nagpur in Maharashtra, India, the ruins of Nagardan Fort conceal a far more remarkable story than their weathered walls initially suggest. For centuries, the site appeared to be just another abandoned hill fort, scattered across the Deccan landscape. That perception changed when archaeological excavations revealed the remains of an ancient urban centre linked to Nandivardhana, one of the capitals of the Vakataka dynasty during the 4th and 5th centuries CE. Beneath layers of soil, researchers uncovered palace complexes, defensive structures, drainage networks, workshops, luxury goods, coins, and evidence of large-scale urban planning. These discoveries transformed Nagardan from a forgotten fortress into a technological mystery. Archaeologists could clearly see the results of sophisticated engineering, yet many of the techniques and methods behind those achievements remain only partially understood. What makes Nagardan particularly intriguing is that it emerged during a period often described as one of ancient India's golden ages. The Vakatakas were contemporaries and allies of the Gupta Empire, a civilization famous for advances in mathematics, astronomy, metallurgy, and architecture. Historians possess inscriptions, artworks, and literary records from the era, yet surprisingly little survives regarding the practical, engineering knowledge used to build and operate major urban centres. Nagardan offers a rare opportunity to examine that missing technological layer. The first mystery begins with the fortress itself. At first glance, the defensive walls seem relatively conventional, but closer examination reveals a level of planning that appears unusually advanced for the period. The positioning of entrances, angles of approach, and defensive sectors suggests that builders understood concepts of battlefield control that would later become fundamental in military architecture. Certain sections appear designed to funnel attackers into predictable paths while exposing them to defenders positioned along elevated walls. Similar principles can be observed in much later fortifications across Asia and Europe. Yet Nagardan predates many of those examples by centuries. The question is not whether ancient engineers could build walls. The question is how they developed such sophisticated defensive geometry without surviving military engineering manuals or documented design traditions. Equally fascinating is the site's urban organization. Excavations indicate that different activities were carefully separated into distinct zones. Administrative areas, residential quarters, storage facilities, and production centers occupied planned spaces rather than developing randomly over time. Modern urban planners understand the enormous complexity involved in organizing a city efficiently. Even today, successful urban layouts require surveying, measurement, logistics, and long-term forecasting. Archaeological evidence suggests that Nagardan's builders achieved comparable results using tools that appear remarkably simple by modern standards. No precision instruments have been found. No engineering blueprints survive. Yet the overall arrangement displays a coherence that implies accurate land measurement and coordinated planning over a substantial area. The mystery becomes even more intriguing when water management enters the picture. Nagardan existed in a region where seasonal rainfall dominates the annual water cycle. During monsoon months, large quantities of water arrive rapidly. During dry periods, water becomes a precious resource. Ancient cities often rose or fell based on their ability to manage this challenge. Excavations at Nagardan reveal reservoirs, drainage channels, collection systems, and hydraulic infrastructure designed to regulate both excess water and scarcity. Modern hydrological models demonstrate that even minor miscalculations in reservoir capacity, channel gradient, or drainage volume can lead to catastrophic failure. Yet the settlement appears to have functioned successfully for generations. Researchers can observe the infrastructure itself, but the mathematical principles and accumulated engineering experience behind its design remain largely invisible. The drainage systems present another unresolved puzzle. Across the ancient world, effective drainage was one of the most difficult engineering problems. Water infiltration weakens foundations, damages walls, accelerates erosion, and can ultimately destroy entire settlements. Cities such as Mohenjo-Daro became famous for remarkably advanced drainage networks more than a millennium earlier. Nagadan appears to continue that tradition of hydraulic sophistication. Some excavated channels suggest deliberate attempts to control runoff and prevent structural damage. The builders clearly understood how water moved through the landscape. What remains unclear is how this knowledge was transmitted across generations and whether it existed as formal engineering doctrine or as practical expertise accumulated through centuries of experimentation. The construction materials themselves raise further questions. Archaeologists have identified extensive use of fired bricks, produced on a scale that implies organized manufacturing. Many surviving examples display dimensions that remain surprisingly consistent. Achieving such standardization without mechanized production is difficult. Modern industrial systems rely upon molds, quality control procedures, measurement standards, and continuous supervision. Ancient brickmakers possessed none of these advantages, yet evidence suggests they were able to produce large quantities of building materials with relatively little variation. This consistency hints at the existence of technical standards that governed construction projects throughout the settlement. Some researchers argue that standardization may be one of the strongest indicators of technological sophistication. In engineering, repeatability often matters more than isolated innovation. A civilization capable of producing thousands of nearly identical construction components possesses a level of organizational and technical discipline that extends beyond simple craftsmanship. The mystery is that no written technical codes from Nagardan have survived. The physical evidence suggests standards existed. The documents that explained those standards have vanished. Beneath all of these achievements lies an even deeper question: labor organization. Large-scale construction projects require more than engineering knowledge. They demand administration, logistics, scheduling, supply chains, workforce management, and resource allocation. Modern infrastructure projects rely upon computers, communication networks, written records, and specialized management systems. Ancient Nagardan possessed none of these technologies. Nevertheless, it successfully coordinated the construction of fortifications, public buildings, water systems, and urban infrastructure. Archaeologists can estimate the volume of material moved, the labor required, and the complexity of the finished structures. What they cannot fully explain is the organizational mechanism that made such projects possible. Comparisons with other ancient centers make the puzzle even more striking. The Roman Empire left extensive written records describing aspects of engineering and construction. Ancient China preserved technical manuals covering architecture, hydraulics, and administration. In contrast, much of the practical engineering knowledge behind Nagardan appears to have disappeared. The city survives as evidence of technological capability, yet the intellectual framework that produced those achievements remains largely absent from the historical record. It is similar to discovering a modern aircraft while losing every manual, formula, and training program associated with its creation. Excavated artifacts add another layer to the mystery. Luxury objects, coins, ornaments, and imported materials indicate that Nagardan participated in broader economic networks extending across the Indian subcontinent. Such trade connections required reliable roads, storage systems, taxation mechanisms, and administrative oversight. The city was not an isolated fortress. It functioned as a regional hub integrated into a larger political and economic landscape. The sophistication implied by these networks further reinforces the impression that a substantial body of technical and administrative knowledge once existed here. Perched in the Andes of southern Peru at an elevation of more than 3,500 meters above sea level, Vilcashuaman is often seen as just another ancient Inca ruin. Yet among its stone terraces stands a massive ceremonial platform known as the Ushnu, a structure so precisely integrated into the landscape that archaeologists still debate how it was designed, surveyed and constructed without modern instruments. Following the Spanish conquest in the 16th century, much of Vilcashuaman was dismantled and built over. Colonial churches rose directly on top of Inca foundations. Archaeological investigations conducted during the 19th and 20th centuries gradually revealed that beneath the colonial town survived one of the most important provincial capitals of the Inca Empire. What emerged was not merely a settlement. It was a carefully planned administrative centre, positioned along the vast royal road system known as the Capacnan, connecting Cusco with distant regions of the empire. The first mystery begins with the city's layout itself. Vilcashuaman occupies rugged mountainous terrain where construction is naturally difficult. Modern engineers facing such conditions would first perform topographic surveys, calculate slope stability, establish reference points, and create detailed maps before beginning construction. The Inca possessed none of these technologies in a modern sense. No compasses, no steel measuring instruments, no theodolites, and no written engineering manuals. Yet the city displays remarkable organization. Roads converge towards central ceremonial spaces. Major structures align with one another across uneven terrain. Terraces, retaining walls, plazas, and ceremonial architecture function as components of a unified design rather than isolated buildings. Researchers have long questioned how Inca planners achieved this level of spatial control. Similar questions arise at Machu Picchu, Ollantaytambo, and Sacsayhuaman, but Vilcashuaman presents a unique challenge because its urban design appears to combine administrative, ceremonial, and astronomical functions within a relatively compact area. Modern archaeological mapping suggests intentional geometric planning rather than gradual organic growth. The settlement appears to have been conceived as a complete project before construction began. If true, the planners possess surveying capabilities far more sophisticated than traditionally assumed. At the heart of the site stands the structure that continues to fascinate archaeologists more than any other, the Ushnu. Rising in a series of massive stone terraces, the monument dominates the surrounding landscape. Today it resembles a stepped pyramid, but that description barely captures its complexity. The word Ushnu appears throughout the Inca world. Historical records describe ceremonial platforms used by rulers for rituals, political gatherings, astronomical observations, and state administration. Yet the Vilcashuaman Ushnu is among the largest and most impressive examples ever constructed. This immediately creates a problem. If the structure was merely ceremonial, why invest such extraordinary resources into its construction? Transporting stone blocks to an elevation exceeding 3,500 meters required enormous labor. Building terraces capable of supporting large gatherings demanded advanced understanding of load distribution and foundation stability. Maintaining geometric consistency throughout multiple levels required precise planning. The scale appears excessive for a simple ceremonial stage. Some researchers suggest the Ushnu functioned as a symbolic model of the Inca cosmos. Others argue it served as an administrative command center, where imperial authority was displayed before regional populations. A more intriguing possibility involves astronomy. Across the Andes, many ceremonial structures exhibit alignments with solar events such as solstices and equinoxes. Several investigations have suggested that Ushnus may have acted as observation platforms linked to calendrical calculations. If the Vilcashuaman Ushnu performed such a role, then its dimensions, orientation and position may have been determined by celestial observations accumulated over generations. The challenge is that definitive proof remains elusive. Archaeologists can measure the monument, reconstruct its geometry, and model sightlines using modern software. What they cannot fully recover is the intellectual process that originally guided its design. The giant Ushnu remains one of the clearest examples of a structure whose physical form survives while its engineering logic has largely vanished. Another mystery lies in the stonework itself. Like many elite Inca structures, parts of Vilcashuaman display finely fitted masonry. Individual stones interlock with extraordinary accuracy despite the absence of mortar. The joints between blocks often appear astonishingly tight. This achievement becomes even more remarkable when compared with construction methods elsewhere in the ancient world. The Egyptians used large limestone blocks, but relied heavily on gravity and mass. The Romans frequently employed mortar to compensate for irregularities. Medieval builders often concealed imperfections beneath plaster. The Inca pursued a different solution. They shaped stones so precisely that neighboring blocks effectively locked together. Experimental archaeology has attempted to replicate this process using stone hammers and abrasive materials. The results demonstrate that such precision is possible. However, achieving it consistently across large structures requires immense labor and exceptional craftsmanship. The unanswered question is efficiency. How did Inca builders produce such accuracy on a scale large enough to construct entire administrative centers? No surviving records describe the exact workflow. No detailed construction manuals have been found. The techniques were evidently effective, yet the knowledge system behind them remains largely invisible. Peru sits along one of the most seismically active regions on Earth. Major earthquakes have repeatedly struck the Andes throughout recorded history. Despite this reality, many Inca structures have survived remarkably well. Vilcashuaman offers valuable clues. Walls frequently lean slightly inward. Doorways often adopt trapezoidal shapes. Stone blocks interlock in ways that permit limited movement during seismic activity. Modern structural analysis indicates that these characteristics can improve earthquake resistance. The mystery is not whether the system works. The mystery is how the Inca discovered it. No mathematical theory of seismic engineering existed. No modern geological science existed. Yet repeated architectural solutions appear throughout the empire. Some researchers argue that centuries of accumulated experience gradually refined construction methods through observation and adaptation. Others believe the consistency across distant regions implies a more organized transfer of engineering knowledge. Either explanation raises further questions about how technical expertise was preserved and communicated across an empire stretching thousands of kilometers. Vilcashuaman's construction may be even more remarkable than its design. Massive stone blocks were quarried, transported, and assembled in rugged mountains without modern machinery. The Inca had no wheeled transport or powerful draft animals. Although llamas carried small loads, large-scale construction relied mainly on human labor. Like Machu Picchu, Ollantaytambo, and Sacsayhuaman, Vilcashuaman demonstrates how Inca engineers achieved extraordinary results with simple tools. The mystery is not that it was built, the evidence is clear, but how such an effective logistical system made it possible. What do you think? Was the giant Ushnu primarily a ceremonial monument, an astronomical observatory, a political command center, or something else entirely? Share your theory in the comments below. Sanathi was never supposed to be found this way. In the late 20th century, workers dismantling portions of an old temple near the Bhima River in northern Karnataka, India, began uncovering carved limestone slabs hidden inside later structures. What emerged surprised archaeologists. Beneath the medieval layers lay the remains of one of the largest Buddhist centers ever discovered in southern India. a monumental stupa complex dating back nearly 2,000 years to the Satavahana period. The discovery transformed Sanathi from an obscure village into one of the most important archaeological sites in India. Yet the deeper researchers investigated the ruins, the more difficult it became to explain the engineering knowledge that had made such a complex possible. Unlike famous ancient mysteries centered on lost treasures or legends, the mystery of Sanathi is rooted in technology. How did builders working nearly 2 millennia ago create massive stone monuments, transport enormous quantities of material, achieve remarkable geometric precision, and construct foundations capable of surviving centuries of environmental stress, while leaving behind almost no record of the methods they used? The first puzzle appears in the scale of the main stupa itself. Archaeological excavations reveal that the structure originally measured approximately 36 meters in diameter, making it comparable in size to some of the largest Buddhist stupas known from ancient India. Such dimensions required not only vast quantities of stone and brick, but also an advanced understanding of load distribution. A circular monument of this scale concentrates tremendous weight toward its center. Modern engineers calculate that even a modest stone structure of similar dimensions can exert thousands of tons of downward force on its foundations. Yet, despite centuries of weathering, flooding, and human modification, large portions of the underlying platform remain stable. This is particularly surprising because the Pima River basin consists largely of alluvial soils, sediments that are often prone to settlement and shifting. Many modern structures built on comparable terrain require deep foundations, reinforced concrete, and extensive geotechnical surveys. The builders of Sanathi possessed none of these technologies. Nevertheless, they created a platform capable of supporting a monument that survived for nearly 2,000 years. The mystery deepens when researchers examine the geometry of the site. Excavated foundations reveal an extraordinary degree of symmetry. Measurements indicate that many architectural elements maintain alignment accuracy within a few centimeters, despite spanning tens of meters. Achieving such precision without laser surveying equipment, optical instruments, or modern measuring tools remains difficult to reconstruct. Historians know that ancient Indian builders used cords, wooden measuring rods, and geometric principles described in early architectural traditions. However, the consistency observed at Sanathi suggests a level of field application that exceeds what many scholars once assumed possible. Similar precision is often associated with later achievements such as the Roman Pantheon, whose dome measures over 43 meters in diameter, or the carefully planned urban grids of Roman colonial cities. Yet Sanathi demonstrates that sophisticated geometric planning was also being applied within Buddhist architectural traditions, hundreds of kilometers from the major imperial centers of the ancient world. One of the most intriguing engineering questions concerns the stone itself. The site contains thousands of carved limestone blocks, many decorated with reliefs, inscriptions, and architectural details. Limestone may appear easy to work compared with granite, but it presents its own challenges. The material can fracture unpredictably under stress, particularly when thin decorative elements are carved into its surface. Nevertheless, the artisans of Sanathi produced relief panels featuring intricate human figures, animals, floral motifs, and narrative scenes with remarkable consistency. Some carvings exhibit straight lines, smooth curves, and symmetrical forms that would challenge even skilled stoneworkers today using hand tools. Experimental archaeology has attempted to reproduce similar work using reconstructed ancient tools. Results suggest that the labor investment required would have been enormous. The question therefore becomes not whether ancient artisans could carve the stone, but how they organised production on such a large scale. The site hints at a highly specialised workforce operating under standardised methods, yet no workshop manuals, training records or technical texts survive to explain how this system functioned. Transportation presents another major mystery. A monument as large as the Sanathi Stupa required thousands of tons of construction material. While some stone could have been obtained locally, geological studies indicate that certain materials originated from sources located considerable distances away. Moving heavy stone blocks across ancient landscapes is never a simple task. For comparison, researchers estimate that transporting a single block weighing several tons can require dozens of workers using sledges, rollers, or draft animals. Ancient Egyptians solved similar challenges when constructing pyramids, while Romans relied on extensive road networks and specialized transport systems. Yet no comparable infrastructure has been identified around Sanathi. The Bhima River may have served as a transportation corridor, but seasonal fluctuations in water levels would have complicated navigation. The logistics necessary to coordinate extraction, transport, storage, and construction remain largely invisible in the archaeological record. What survives is the finished monument, not the technological system that created it. Perhaps the most unexpected discovery at Sanathi emerged from the carved panels themselves. Among the artifacts recovered were rare depictions associated with Emperor Ashoka, one of the most influential rulers in Indian history. These images are significant because Ashoka lived centuries before the construction of much of the visible Satavahana complex. Their presence suggests that cultural memories, artistic traditions, and possibly architectural knowledge were transmitted across vast stretches of time. This raises an important technological question. How was specialized knowledge preserved and communicated in a largely pre-industrial society? Modern engineering depends on textbooks, blueprints, formal education, and digital records. Ancient builders relied on oral traditions, apprenticeships, and practical experience. Yet the continuity visible at Sanathi implies a remarkably stable system for preserving technical expertise across generations. The monument itself may represent the surviving product of a knowledge network that has otherwise vanished completely. Researchers have also become fascinated by the orientation of the complex. Surveys indicate that major structures follow deliberate spatial arrangements rather than random placement. Certain architectural axes appear aligned with celestial events or significant solar positions. Such alignments are not unique to Sanathi. Ancient monuments from Stonehenge in Britain to Chichen Itza in Mexico demonstrate sophisticated observational astronomy. What makes Sanathi interesting is the integration of these alignments into a large religious and ceremonial landscape. Establishing accurate orientations requires repeated observations, reliable measurement systems, and long-term planning. Even small errors can accumulate over large distances. The consistency observed at the site suggests that ancient surveyors possessed methods capable of achieving a level of accuracy that continues to impress modern researchers. Another unresolved issue concerns environmental resilience. Northern Karnataka experiences intense seasonal variation. Temperatures frequently exceed 40 degrees Celsius during summer months, while monsoon rains can produce severe flooding. Such conditions are notoriously destructive to exposed masonry. Water infiltrates cracks, dissolves minerals, weakens mortar, and accelerates structural decay. Yet significant portions of the Sanathi complex endured for centuries before being buried or repurposed. Material scientists studying ancient construction techniques often emphasize that durability depends not only on materials, but also on design. Drainage systems, foundation preparation, joint construction, and load management all contribute to longevity. The surviving remains of Sanathy suggest that its builders understood these principles far better than historians once believed. Exactly how they acquired that knowledge remains unclear. In Volterra, Tuscany, Italy, ancient stones preserve a technological mystery that refuses to disappear. Long before Rome dominated the Mediterranean, the Etruscans transformed this rugged summit into a carefully planned sacred and political centre. Today, archaeologists call it the Volterra Acropolis. At first glance, the ruins appear modest compared with the pyramids of Egypt or the terraces of Machu Picchu. Yet beneath the surviving foundations lies a deeper puzzle. The mystery is not what the Etruscans built, but how they achieved such sophisticated engineering while leaving behind almost none of the technical knowledge that made it possible. The Acropolis occupies the highest point of Volterra, a city that rises more than 500 meters above sea level. Archaeological excavations conducted during the 20th century reveal temples, roads, foundations, drainage systems, and evidence of urban planning dating primarily to the Hellenistic Etruscan period between the 4th and 2nd centuries BCE. What researchers uncovered was not merely a collection of buildings, but an integrated engineering system constructed on one of the most challenging landscapes imaginable. The location itself immediately presents a problem, as Volterra stands atop a geological formation known for instability. Even today, portions of the surrounding terrain experience erosion, landslides, and gradual slope movement, prompting modern engineers to continuously monitor the region because the underlying soils and sedimentary layers can become unstable under changing environmental conditions. Yet, more than 2,000 years ago, Etruscan builders selected this difficult terrain and successfully erected monumental structures capable of surviving centuries of weather, earthquakes, and human occupation. The first mystery emerges from the site's geometry, as when archaeologists mapped the Acropolis, they discovered evidence of deliberate planning rather than organic growth. Building orientations, street alignments, and temple placements reveal consistent geometric relationships, which may sound ordinary until one considers the terrain. Creating regular alignments on a flat plain is relatively straightforward, but doing so on an uneven hilltop requires surveying techniques capable of compensating for changing elevations, irregular rock formations, and shifting slopes. Modern surveyors use total stations, laser scanners, GPS systems, and digital terrain models. Yet Etruscan engineers possessed none of these technologies. Nevertheless, the layout demonstrates a level of spatial organization, suggesting careful measurement and advanced planning. Comparisons with contemporary settlements reveal how unusual this achievement may have been, as many Iron Age communities expanded incrementally, producing irregular street networks that reflected local geography, whereas Volterra displays evidence of intentional organization resembling urban planning traditions later perfected by Roman engineers. How Etruscan surveyors achieved this accuracy remains largely unknown. The puzzle deepens when researchers examine the foundations, as unlike modern construction projects, Etruscan builders could not conduct geotechnical drilling programs or computer-based stability analyses, nor did they possess mathematical models describing soil mechanics. Yet the placement of major structures suggests a remarkable understanding of the hill's geological behavior. Several surviving foundations appear positioned on the most stable portions of the summit, leading some archaeologists to argue that centuries of accumulated empirical knowledge allowed Etruscan builders to identify load-bearing zones through observation alone, while others believe their practical understanding of geology may have been far more sophisticated than surviving evidence suggests. the challenge becomes clear when compared with modern construction standards, as contemporary engineers often spend months evaluating ground conditions before placing large public buildings, whereas the Etruscans somehow achieved long-term structural stability without access to any of the instruments modern engineers consider essential. Water management introduces another layer of mystery, as ancient builders understood that water is often more dangerous than gravity. Rainwater infiltrating soil can trigger erosion, weaken foundations, and destabilize slopes, making control of runoff critical on elevated sites such as Volterra. Excavations have revealed traces of drainage systems integrated directly into the Acropolis, including channels, carefully graded surfaces, and engineered pathways designed to guide water away from important structures. The remarkable aspect is that much of this hydraulic system was effectively invisible, as instead of relying solely on large open canals, the builders appear to have manipulated slopes, surface gradients, and subsurface features to manage water movement. Modern civil engineers frequently describe drainage as one of the most difficult aspects of hillside construction, because failures often remain hidden until catastrophic damage occurs. Yet the fact that portions of the Acropolis remained functional for centuries suggests that the hydraulic design was highly effective. Perhaps nowhere is the technological mystery more fascinating than in the structure archaeologists designate as Temple A, which is among the most significant discoveries on the Acropolis because it offers clues about a possible system of architectural standardization. Detailed measurements of the foundations reveal recurring dimensions, repeated spacing patterns, and proportional relationships that appear unlikely to be accidental, leading some researchers to propose a provocative possibility that the builders may have employed a modular design system. In modern architecture, modular construction involves creating structures from standardized units governed by predetermined measurements, simplifying planning, improving consistency, and reducing construction errors. And this concept is fundamental to modern engineering and manufacturing. Evidence from Temple A suggests the Etruscans may have applied a similar principle more than 2,000 years ago, as certain foundation dimensions appear to follow recurring ratios. Column spacing may have been derived from a common measurement unit, and structural elements seem organized according to repeatable geometric rules. If this interpretation is correct, the implications are enormous, indicating that Etruscan builders were not merely skilled craftsmen responding to local conditions, but may have possessed an abstract architectural framework capable of generating complex structures through standardized design principles. The mystery lies in the absence of documentation, as no surviving manuals explain the system, no mathematical texts describe the measurements, and no architectural treatises equivalent to those later written by Roman engineer Vitruvius have been discovered. The stones suggest a coherent methodology, yet the methodology itself has vanished, creating one of archaeology's most intriguing paradoxes, in which the physical output survives while the intellectual process behind it remains largely invisible. The stonework itself raises additional questions, as many blocks used throughout Volterra display surprisingly precise workmanship with tool marks indicating systematic cutting techniques, surfaces prepared with consistency, and joints often fitting closely despite the absence of modern machining equipment. Experimental archaeologists attempting to replicate ancient stoneworking methods frequently encounter an uncomfortable reality, as even with access to modern understanding of materials and mechanics, reproducing ancient craftsmanship using period-appropriate tools can be extraordinarily labor-intensive. The issue is not whether ancient workers could achieve such results, as clearly they did, but whether they possessed organizational methods, workforce management systems, and construction procedures more advanced than traditionally assumed. Overlooking the Atlantic coast of northwestern Spain at the mouth of the Minho River in Galicia lies the Castro of Santa Trega. More than 2,000 years ago, an entire stone city was built on a windswept mountain summit. Today, archaeologists can see the walls, they can map the streets, but they still cannot fully explain how its builders achieved such remarkable engineering precision without written plans, advanced instruments, or sophisticated machinery. Although local people had long known of the ruins, systematic archaeological excavations began in the early 20th century, and what researchers uncovered was astonishing. Hundreds of stone structures spread across nearly 20 hectares, making Santa Trega one of the largest known Iron Age settlements in the Iberian Peninsula. The discovery transformed understanding of the ancient Castro culture, as what had once been viewed as scattered tribal communities suddenly appeared capable of creating large, highly organized urban settlements. The first mystery begins with location, as most ancient civilizations preferred valleys, river plains, or fertile lowlands, because these environments reduced construction costs and simplified agriculture. Yet Santa Trega ignored those advantages entirely. The settlement occupies a mountain rising approximately 340 meters above sea level, where strong Atlantic winds strike the summit throughout the year, and rainfall in Galicia frequently exceeds 1,000 millimeters annually, sometimes reaching nearly 2,000 millimeters in certain regions. Modern engineers understand the difficulties of building on steep terrain, where every structure requires stable foundations, water runoff must be controlled, landslides must be prevented, and access routes must remain functional. Yet the ancient builders transformed the mountain into a functioning urban landscape. Researchers estimate that extensive leveling and terrace construction would have been necessary before many of the houses could even be built, and massive quantities of stone had to be moved across slopes without wheel transport systems, comparable to later Roman infrastructure, leaving the question unresolved. How was such a large-scale landscape engineering project organized and executed by an Iron Age society? Among all the mysteries of Santa Trega, perhaps none is more intriguing than the remarkable precision of its circular architecture, as hundreds of houses discovered throughout the settlement are round or oval in shape, appearing simple at first glance, but revealing something unexpected upon closer examination. Many walls follow smooth geometric curves with impressive consistency, and their circular plans are not random approximations, but instead display a level of regularity suggesting intentional measurement. Modern surveyors can create perfect circles using lasers, steel tapes, and digital instruments. Yet the builders of Santa Trega possessed none of these technologies, and even with a simple rope and stake method, maintaining consistent geometry across hundreds of structures would require a standardized construction process and skilled builders. Though no written manuals survive and no measuring tools have been found to explain the system, archaeologists often compare these houses with circular structures found throughout Celtic Europe, but Santa Trega presents a particularly concentrated example, where entire neighborhoods display repeated geometric patterns that appear to follow shared design principles. The mystery deepens when considering construction accuracy, as stone walls composed of irregular granite blocks somehow maintain smooth, external curves over significant distances, requiring continuous adjustment during construction, where every stone placement affects the final geometry. Modern masonry studies show that curved walls demand more planning than straight walls, because each block must accommodate changing angles, increasing labor requirements and complexity, suggesting that the builders were not simply stacking stones, but were shaping space according to geometric rules that remain largely invisible to archaeology. The circular houses may have served practical purposes extending far beyond aesthetics, as aerodynamic studies demonstrate that circular structures experience reduced wind pressure compared with rectangular buildings, with strong gusts being diverted around curved surfaces rather than striking flat walls directly. This is particularly relevant at Santa Trega, where the settlement faces the Atlantic Ocean and experiences powerful coastal winds, and modern architects designing structures for hurricane-prone regions sometimes employ similar principles. Did Iron Age builders understand aerodynamic efficiency? Probably not in mathematical terms, but centuries of observation may have allowed them to recognize which building forms survived storms most effectively, leading to a fascinating possibility. Empirical engineering developed through generations of experimentation rather than formal science. Water may represent Santa Trega's greatest technical challenge, as a settlement containing hundreds or perhaps thousands of inhabitants required reliable water supplies, despite being located on a mountain summit, and equally important was drainage. Heavy rainfall can destroy settlements through erosion, as water flowing downhill gains energy, carving channels and undermining foundations. Yet despite this threat, large portions of Santa Trega remained stable for more than 2 millennia. Researchers have identified pathways, terraces, and open spaces that may have functioned as components of an integrated drainage network. And rather than relying on monumental canals like those of ancient Rome, the settlement appears to have used subtle topographic control. In modern engineering terms, this resembles passive water management, where gravity performs the work and the landscape itself becomes infrastructure, though the challenge remains that much of the original system has vanished, leaving archaeologists to see fragments while struggling to reconstruct the complete hydraulic design. Another mystery emerges when viewing Santa Trega from above, as the settlement does not appear chaotic but instead shows buildings clustering into organized groups, pathways connecting neighborhoods, open areas occurring in strategic locations, and circulation routes that seem intentional. This raises a difficult question. How did planners coordinate construction across such a large settlement without written architectural drawings? Today, urban planning relies on maps, measurements, and standardized documentation, yet no evidence suggests that Santa Trega possessed comparable systems, and still the city functions as an integrated whole. Comparisons with other Iron Age sites reveal that Santa Trega was not merely a collection of isolated houses, but behaved more like a planned urban environment, though the intellectual process behind that planning remains invisible. One of the strongest indicators of advanced technical knowledge is standardization, and at Santa Trega, researchers repeatedly encounter recurring architectural patterns where house dimensions often fall within similar ranges. Construction methods show notable consistency, and building layouts share common characteristics. Such uniformity rarely emerges spontaneously, as in most societies, standardization reflects the transmission of specialized knowledge. Where skilled builders teach apprentices, techniques become refined, and construction traditions persist for generations. But here lies the mystery. The knowledge survived long enough to build an entire city, then it disappeared, leaving no surviving texts to explain the methods, no engineering manuals, and no architectural diagrams to reveal how measurements were made, with only the finished products enduring. Xi'an City Wall is one of the largest and best preserved military fortifications ever built, standing in the heart of Xi'an, Shaanxi Province, China. Millions of visitors walk its massive ramparts every year, yet few realize that hidden beneath its bricks lies a technological puzzle that continues to fascinate engineers, materials scientists, and historians alike. Stretching nearly 13.7 kilometers around the old capital, rising approximately 12 meters high and reaching up to 18 meters wide at its summit, the wall appears to be a straightforward medieval defensive structure. But when researchers began studying its construction methods in detail, They discovered evidence of engineering sophistication that seems far ahead of what many assume was possible in the 14th century. The deeper scientists look into the wall's materials, drainage systems, geometry, and structural durability, the more difficult it becomes to explain how builders working over 600 years ago achieved such remarkable results without modern technology. The modern investigation of the wall began during restoration efforts in the 20th century. Archaeologists, architects, and structural engineers expected to find ordinary medieval construction techniques. Instead, they encountered a structure whose performance often exceeded modern expectations. Excavations revealed an enormous rammed earth core covered by millions of specially manufactured bricks. Material analyses uncovered unusual binding agents. Hydrological studies exposed an unexpectedly advanced drainage network. Structural surveys showed an astonishing level of geometric precision across a perimeter nearly 14 kilometers long. Rather than solving the mystery, each discovery raised new questions about the knowledge possessed by Ming Dynasty engineers. Perhaps the most intriguing mystery centers on the wall's construction materials. At first glance, the bricks seem ordinary. However, laboratory analysis revealed traces of a unique mortar mixture unlike most medieval building compounds. Scientists discovered that builders mixed slaked lime with sticky rice soup, creating a hybrid organic-inorganic composite material. The key ingredient appears to be amylopectin, a complex carbohydrate found in glutinous rice. When combined with lime, this substance forms microscopic structures that significantly improve strength, durability, and water resistance. Modern material scientists often describe this mixture as one of the earliest examples of engineered composite construction materials. Tests have shown that sticky rice mortar possesses superior bonding strength compared with many traditional lime mortars. Some experiments demonstrated compressive strengths exceeding those of standard historical mortars by significant margins. The material also exhibits remarkable resistance to water infiltration, one of the primary causes of deterioration in ancient masonry structures. What remains unexplained is how ancient builders discovered such a formula in the first place. There is no surviving scientific document describing experimental development. No engineering manual explains why glutinous rice was selected or how the proportions were determined. The mixture appears too effective to be accidental. In modern laboratories, researchers spend years developing composite materials through controlled testing. Yet centuries ago, Chinese builders somehow produced a mortar capable of surviving hundreds of years of rain, frost, temperature fluctuations, and even earthquakes. Comparisons with other ancient building materials make the mystery even more compelling. Roman engineers famously used volcanic ash in their concrete, creating structures that remained standing after 2 millennia. Researchers studying Xi'an's mortar often draw parallels to Roman concrete because both technologies combine natural materials in ways that dramatically improve performance. Yet, while Roman concrete relied on volcanic pozzolans, Xi'an's builders developed an entirely different solution based on organic chemistry. Two civilizations separated by thousands of kilometers arrived at distinct advanced material technologies, each producing structures that outlived countless generations. The wall's extraordinary longevity cannot be explained by mortar alone. Beneath the brick surface lies an immense rammed earth core, constructed through the systematic compression of countless layers of soil. Historical records indicate that each layer was compacted repeatedly before the next was added. Modern geotechnical studies reveal density levels that continue to impress engineers. The resulting structure behaves differently from a solid stone wall. Instead of resisting forces through rigidity alone, it absorbs and redistributes stress throughout its mass. This characteristic becomes particularly important when considering seismic activity. Shanxi Province has experienced numerous earthquakes throughout its history, including the catastrophic 1556 Shanxi earthquake, often regarded as the deadliest earthquake ever recorded. Modern estimates suggest a magnitude near 8.0, with casualties potentially exceeding 800,000 people. Entire settlements disappeared, countless structures collapsed, yet substantial portions of Xi'an's defensive system survived. Engineers studying the wall today suggest that the combination of dense rammed earth and flexible masonry may have functioned as a primitive seismic-resistant design. The earthen core absorbs vibration energy while the brick exterior distributes stress. This concept resembles principles employed in some modern earthquake engineering systems. Whether Ming builders consciously understood these effects remains unknown, but the wall's survival raises questions about the depth of empirical knowledge accumulated through centuries of construction experience. Another unresolved puzzle concerns water management. Water is one of the greatest enemies of large earthen fortifications. If rainwater penetrates the interior, erosion gradually weakens the structure from within. Given Xi'an's dimensions, even moderate storms could generate enormous volumes of runoff. Yet the wall has resisted serious water damage for centuries. Detailed surveys have revealed a sophisticated drainage system integrated throughout the structure. Numerous outlets, channels, and slopes direct water away from critical areas. Engineers mapping the system discovered that drainage points were carefully positioned to prevent accumulation. Surface gradients guide water toward designated exits while minimizing infiltration into the core. The precision of this hydraulic design is difficult to explain. Modern civil engineers rely on mathematical models, surveying instruments, and hydraulic calculations when designing drainage systems for large infrastructure projects. Ming engineers possessed none of these tools in their modern form. Nevertheless, they created a network capable of protecting one of the largest urban fortifications in the world. Whether this achievement resulted from advanced practical experience, lost engineering traditions, or sophisticated geometric planning remains a subject of debate. Geometry presents another mystery. Satellite imagery reveals the enormous scale and symmetry of the wall. The enclosure forms an impressively regular defensive perimeter around the ancient city. Maintaining geometric consistency across nearly 14 kilometers would challenge even modern survey teams without proper equipment. Builders of the 14th century lacked GPS, aerial photography, laser measurements, and digital mapping. Yet measurements indicate surprisingly low deviations across major sections of the fortification. Historians believe surveyors relied on astronomical observations, ropes, measuring rods, and geometric principles. However, the level of precision achieved suggests organizational capabilities and technical knowledge beyond what many people associate with medieval construction. The military design of the wall adds another layer to the mystery. Nearly 100 defensive bastions project outward from the main structure. These positions were arranged to maximize overlapping fields of fire, allowing defenders to attack approaching enemies from multiple angles. Military historians often note that the layout minimizes blind spots and optimizes defensive coverage. Such efficiency resembles modern concepts of defensive geometry and operational planning. The arrangement appears less like a collection of independent towers and more like a carefully optimized system. Determining the ideal spacing of defensive positions across a massive perimeter would have required extensive planning. Yet little evidence survives explaining the calculations or design methodologies employed by the engineers responsible. What do you think? Was the extraordinary durability of Xi'an City Wall the result of centuries of accumulated experience? Or did Ming engineers possess construction knowledge that has since been lost? Share your thoughts in the comments below.